Something is wrong. Not wrong in the way a calculation fails. Not wrong in the way a theory needs a minor adjustment. Not wrong in the way science occasionally stumbles before finding its footing again. Something is wrong at a level so deep, so foundational, so threaded through the very fabric of how we understand existence, that the word wrong barely begins to carry the weight of what we're talking about. The universe you think you live in, the one made of stars and atoms and time and cause and effect, that universe may not be what it appears to be. And the people who have spent their entire lives trying to understand it, the most brilliant and rigorous minds our species has ever produced, are beginning to admit something they have resisted saying out loud for decades. They are beginning to admit that the map they built, the map that was supposed to describe everything, may not match the territory at all. You wake up every morning under the assumption that the world operates according to rules. The sun rises because the earth rotates. Objects fall because of gravity. Time moves forward because that is what time does. You trust these things not because you tested them yourself, but because the entire architecture of modern civilization rests on them. Your phone works, your car moves. The bridge you drive over doesn't collapse. Science made all of that possible, and so you extend to science a kind of deep, almost unconscious trust. You assume that the same system of thought that figured out how to split an atom and map the human genome and land a spacecraft on a rock, hurtling through the void, also knows, more or less, what the universe fundamentally is. That assumption, it turns out, is one of the most dangerous things you will ever believe. This is not a story about one mistake. It is not about a single experiment that went wrong or a theory that needs refinement. It is about something far more unsettling, a pattern of failure that stretches across every major branch of physics that shows up in data collected by the most sophisticated instruments ever built, and that refuses to go away no matter how cleverly scientists try to explain it. The story of modern physics is not a triumphant march toward final understanding. It is, at this particular moment in history, more like standing in a hallway that you were certain led somewhere important, only to discover that the door at the end opens onto nothing, or worse, opens onto a space that shouldn't exist at all. To understand why this matters, you need to feel what it was like to believe we had it figured out. Not long ago, in the arc of human history, the universe was terrifying precisely because it was incomprehensible. Lightning was not electricity. It was the fury of gods. Plagues were not bacteria. They were divine punishment. The sky was not a field of nuclear fusion happening billions of light years away. It was a canopy of lights placed there by forces beyond human understanding. And then, over the span of a few hundred years, something extraordinary happened. Human beings started asking different kinds of questions. They started measuring. They started predicting. They started building machines that worked exactly as the equations said they should, again and again and again. And slowly, the terrifying incomprehensibility of the universe began to seem like it was yielding, like the fog was lifting, like the deepest secrets of existence were finally becoming legible. By the 20th century, that feeling of understanding had reached what felt like a peak. Two monumental theories had been built, theories so precise and so powerful that they changed not just science, but the entire human experience of reality. The first was general relativity, Einstein's breathtaking reimagining of gravity, space, and time. He showed that the universe is not a stage on which events happen. It is itself a dynamic, malleable structure, a four-dimensional fabric that bends and curves and stretches in response to mass and energy. The second was quantum mechanics, the strange and wildly counterintuitive description of the world at the smallest scales, where particles don't have definite positions until they're observed, where a single object can be in two places at once, where the act of measurement itself changes what is being measured. These two theories, between them, describe the universe from the largest scales imaginable down to the smallest. They were tested thousands of times. They passed every single test, and together, they gave humanity the most confident picture of reality it had ever held. There was a period, particularly in the latter half of the 20th century, when physicists spoke with a quiet confidence that bordered on certainty. The standard model of particle physics, a catalog of the fundamental building blocks of matter and the forces that govern their interactions, had been verified with extraordinary precision. GPS satellites worked because they accounted for relativistic effects. Semiconductor chips functioned because engineers understood quantum behavior. Nuclear reactors ran because we understood how matter converts to energy. Every prediction we made, every test we ran, every instrument we built, they all confirmed the same story. The universe, vast and ancient and strange as it was, appeared to be operating according to laws we had successfully decoded. And somewhere in the background of human consciousness, a quiet voice started whispering that maybe, just maybe, we were close to a theory of everything. That voice was intoxicating, and it was wrong. The first crack appeared so quietly that most people didn't notice it. It came not from some dramatic experiment or catastrophic failure, but from a number. A single, deceptively simple number that described how fast the universe is expanding. You see, we have known since the 1920s, since Edwin Hubble first mapped the recession of distant galaxies, that the universe is not static, it is expanding. Every galaxy is moving away from every other galaxy, like raisins in a rising loaf of bread, each one retreating from all the others as the space between them stretches. The rate of that expansion is described by a quantity called the Hubble constant, and for decades measuring this number accurately was considered one of the great goals of observational cosmology. If we knew the Hubble constant, we could work backward to the Big Bang, forward to the ultimate fate of the universe and everywhere in between. It was supposed to be an anchor point, a firm number on which much of our understanding of cosmic history could be grounded. The problem is that the Hubble constant isn't behaving like an anchor point. It is behaving like a source of deep, unresolved chaos at the heart of cosmology, because when scientists measure it in two very different ways, one looking at the early universe, the other looking at the nearby universe, they get two very different answers, not slightly different, not different within the margin of experimental error, significantly, stubbornly, persistently different, in a way that has only become more pronounced as our measurements have become more precise. The early universe measurement, derived from the cosmic microwave background, the faint echo of radiation left over from the Big Bang, gives one value. The nearby universe measurement, using observations of certain types of stars and supernovas as cosmic yardsticks, gives a larger value. The two measurements refuse to agree, and the more accurately we measure, the worse the disagreement becomes. This disagreement has a name. Physicists call it the Hubble tension, and the word tension is doing an enormous amount of work there, carrying all the weight of something that is probably wrong but that no one yet knows how to fix. For a long time, the scientific community hoped it was a measurement error. Perhaps the yardstick stars, called Cepheid variables, were being miscalibrated somehow. Perhaps there was a systematic bias creeping into the data from the early universe. These were reasonable hopes, but as the measurements were checked and rechecked, as independent groups using entirely different methods arrived at the same incompatible values, the hope for a simple fix began to fade. Today, the Hubble tension is considered one of the most serious unresolved problems in cosmology, and some physicists now openly suggest that it is not a measurement problem at all. It is a sign that our model of the universe is wrong, not subtly wrong, fundamentally wrong, in a way that requires new physics we don't yet have. But hold on, because the Hubble tension is only the beginning, and if you think that one crack in the foundation is unsettling, what comes next will make you reconsider the entire building. Because the universe, it turns out, has been keeping secrets for a very long time, and we've been building our models on top of those secrets while pretending they were solid ground. Consider what we call dark matter. This is not a fringe idea. It is a central pillar of modern cosmology, a substance that supposedly makes up approximately 27% of the total energy content of the universe, compared to the ordinary matter, atoms, stars, planets, that makes up less than 5%. The evidence for dark matter's existence is, in its own way, compelling. Galaxies spin in ways they shouldn't if they only contained the visible matter we can detect. The larger structures of the universe, clusters of galaxies, the cosmic web of filaments and voids, couldn't have formed in the time available unless there was significantly more gravitational mass than we can see. Something is out there. Something is pulling on everything, bending light, shaping the architecture of the cosmos. We just have no idea what it is. What is deeply unnerving about dark matter is not that we haven't found it yet. Science is comfortable with mysteries. What is unnerving is how long we have been searching with increasingly sensitive instruments and how completely it has evaded detection. Physicists spent decades building elaborate underground detectors, shielded from cosmic rays deep in old mines, waiting for the hypothetical dark matter particles, the most popular candidates being called WIMPs, weakly interacting massive particles, to register a signal. These detectors became progressively more sensitive. They waited longer. They lowered their detection thresholds further and further, extending their search into regions of particle physics that were theoretically extremely promising. And they found nothing. Not a whisper, not a hint. Complete silence. The LHC, the Large Hadron Collider, the most powerful particle accelerator ever built, has smashed protons together at energies high enough to have definitively produced WIMPs if they existed in the mass ranges that were most theoretically favored. It has found nothing of the kind. Now, the absence of evidence is not the same as evidence of absence, and cosmologists are careful to point that out. Dark matter might exist in forms we haven't yet looked for, or at masses we haven't yet probed, or it might interact with ordinary matter in ways so feeble that our detectors would need to be impossibly sensitive to catch it. These are legitimate scientific arguments, and dark matter remains the leading explanation for why galaxies behave the way they do. But you should feel the unease that is quietly spreading through the astrophysics community, because the most straightforward versions of the dark matter hypothesis, the ones that made specific, testable predictions about what particles we should find and when, have been falsified, and what remains is increasingly vague, a placeholder explanation that says something invisible is there, without being able to say very much about what that something is. And science at its deepest level is supposed to do better than that. There is a competing explanation for the anomalous behavior of galaxies that deserves mention, not because it is universally accepted, but because the fact that it exists at all tells you something important about the state of the field. It is called MOND, Modified Newtonian Dynamics, and it was proposed by Israeli physicist Mordechai Milgram in the 1980s. His idea was radical. Perhaps the strange rotation curves of galaxies don't require dark matter at all. Perhaps Newton's law of gravity, our foundational understanding of how gravitational attraction works, breaks down at the very low accelerations found in the outer regions of galaxies. If gravity weakens more slowly at those scales than Newton predicted, then you could explain the observations without invoking invisible matter. And to a remarkable degree, MOND makes accurate predictions for a wide range of galaxies, predictions that the standard dark matter models sometimes struggle to match. This doesn't mean MOND is correct. It has its own serious problems at larger scales, and it doesn't have the same degree of theoretical grounding as dark matter. But the fact that it works as well as it does, in the domain where it was designed to work, should give you pause. It suggests that either there's dark matter with very specific strange properties, or our understanding of gravity, the force we experience every moment of our lives, the force that governs planetary orbits and galaxy clusters, is incomplete in some deep way we don't yet understand. And then there is the other mystery, the one that might be even stranger, the one that has a name so deceptively simple that it barely hints at the abyss it points toward: dark energy. In 1998, two independent teams of astronomers were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, in order to measure how the expansion of the universe was decelerating. Because of course it was decelerating. Everything in the universe has gravity, and gravity pulls things together, so the expansion that began with the Big Bang should be gradually slowing down. That was the expectation. That was what the physics demanded. That was what every sensible cosmologist predicted. What they found instead rearranged everything. The expansion of the universe was not slowing down. It was speeding up. The universe was accelerating outward, driven by some unknown force or energy that was not just pushing against gravity, but was winning, comprehensively and irresistibly, pulling the fabric of space itself apart at an ever-increasing rate. The discovery was so shocking that it won the Nobel Prize in Physics in 2011. But winning the Nobel Prize doesn't mean we understand it. We gave this thing a name, dark energy, and we assigned it a rough value, representing approximately 68% of the total energy content of the universe. But what it actually is, what mechanism drives it, why it has the precise value it has, we have absolutely no idea. Here is where things become not just puzzling, but philosophically vertiginous. In quantum field theory, the framework that underlies all of particle physics, there is a natural candidate for dark energy. It is called vacuum energy, the energy that exists in empty space itself. Quantum mechanics tells us that the vacuum is not empty at all. It is a seething foam of virtual particles popping in and out of existence, and this activity should carry energy. Physicists can calculate what the vacuum energy should be based on our best theories of particle physics. And when they do that calculation, and here is the number that should make your mind reel, the theoretical prediction is off from the observed value of dark energy by a factor of somewhere between 10 to the power of 60 and 10 to the power of 120. Let that sit for a moment. Not off by a factor of 2, not off by a factor of 100, off by a number with 60 to 120 zeros after it. This discrepancy has been called the worst prediction in the history of physics. It suggests, with brutal clarity, that something is catastrophically, fundamentally wrong with how we think about energy at the quantum level, about the relationship between quantum mechanics and the large-scale structure of the universe, or perhaps about both. And rather than resolving this absurdity, our best theories have simply adjusted parameters to make it disappear from the equations, which is, in the most honest possible terms, a mathematical trick, not an explanation. Something is beginning to take shape here, a pattern that refuses to resolve into anything comfortable. 3 of the largest, most significant cosmological frameworks we have, our understanding of cosmic expansion rates, our model of the matter content of the universe, and our description of the energy that drives the universe's accelerating expansion, are each individually exhibiting severe problems. They don't fit each other cleanly. They don't fit the observations cleanly. They require the insertion of unknown, undetected substances, dark matter, dark energy, that together comprise 95% of the universe. Think about what that means. Our theories of physics have been confirmed with extraordinary precision for the 5% of the universe made of ordinary matter. For the remaining 95%, we have given names to our ignorance and declared it understood. We have essentially said, we know what 5% of the universe is, and for the rest we'll call it dark and assume it's there. And for a while, that seemed like a reasonable placeholder, but now even the placeholder is beginning to show cracks. Because here is what recent observations have been suggesting, with growing insistence: dark energy may not be constant. For decades, the prevailing model, embedded in what cosmologists call the lambda CDM model, the standard model of cosmology, assumed that dark energy was a cosmological constant, a fixed, unchanging property of space itself. Einstein originally introduced this idea, and it became the simplest and most elegant explanation for the accelerating expansion. But data from large-scale galaxy surveys, including the Dark Energy Spectroscopic Instrument, or DESI, have started to hint that this cosmological constant may not be constant at all. It may have been changing over time. And if dark energy is dynamic rather than constant, if it is evolving and shifting through cosmic history, then the standard model of cosmology, the framework that cosmologists have relied on for decades, needs to be rebuilt essentially from scratch. The foundation was never as solid as it appeared. It was always, in some sense, a structure built on a question mark. At this point, you might be thinking, this is all very large-scale stuff, cosmic and distant, affecting the fates of galaxy clusters across billions of light years. What does it have to do with the physics we actually use, the physics that built the modern world? And this is precisely where the story deepens into something genuinely disturbing. Because the problems are not confined to the large scale. They are equally profound at the smallest scales. And they connect to a conflict that sits at the very heart of theoretical physics, one that has been known about for nearly a century and that, despite extraordinary effort, remains completely unresolved. We are talking about the incompatibility between general relativity and quantum mechanics. These are the 2 most successful theories in the history of science. They are also fundamentally irreconcilably in conflict with each other, and the universe doesn't seem to care that we find this uncomfortable. General relativity describes gravity as the curvature of space-time. It is an inherently geometric, smooth, continuous theory. Space-time in Einstein's framework is like an endlessly smooth rubber sheet. It can bend and warp and stretch, but it is always connected, always continuous, always differentiable in the mathematical sense. There are no jumps, no discontinuities, no granularity. Quantum mechanics, on the other hand, is the opposite of smooth. It is fundamentally discrete, granular, probabilistic. At the quantum scale, energy comes in chunks, Positions are fundamentally uncertain, and outcomes are governed by probability rather than determinism. Waves collapse into particles. Particles become waves. Reality at the quantum level is not just counterintuitive, it is structurally incompatible with the smooth, deterministic geometric picture that general relativity paints. When physicists try to combine these two theories, when they try to describe gravity using the tools of quantum field theory, the mathematics breaks down entirely. It produces infinities, nonsensical results, predictions of infinite energy or infinite probability, which is the mathematical equivalent of the universe saying, "You're asking the wrong question." This breakdown is not just an abstract technical problem, it has real, concrete consequences for what we can understand. There are places in the universe where both quantum effects and gravitational effects are simultaneously dominant, places where you cannot use one theory and ignore the other. These places are called singularities. The center of a black hole is a singularity. The very beginning of the universe, the Big Bang, is a singularity. At these points, every equation we have breaks down. General relativity predicts infinite density and infinite space-time curvature. Quantum mechanics gives no coherent answer. The two theories, separately perfect, together produce total mathematical chaos at the most extreme and arguably most important points in cosmic history. We have, in other words, a complete description of the universe everywhere, except in the places where description matters most. Physicists have not been passive in the face of this problem. For nearly a century, some of the most gifted theoretical minds in history have worked on reconciling quantum mechanics and general relativity. The effort has produced beautiful, intricate, and extraordinarily ambitious theories. String theory proposed that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy, and that their different modes of vibration give rise to all the particles and forces we observe. Loop quantum gravity proposed that space-time itself is fundamentally granular at the smallest scale, the Planck scale, woven from discrete loops of quantum geometry rather than being the smooth continuum of Einstein's theory. These approaches are mathematically sophisticated and intellectually breathtaking. They have also, despite decades of development, failed to make a single experimentally confirmed prediction that distinguishes them from what we already know. String theory, at one point, was described by its proponents as the most promising candidate for a theory of everything ever developed. It unified all known forces and particles within a single coherent mathematical framework. It was elegant. It was mathematically rich, generating entire new fields of pure mathematics as a kind of byproduct of its development. But it comes with a price tag that is, to put it gently, astronomical. It requires the existence of extra spatial dimensions, not 3, not 4, but 10 or 11, that are curled up at scales so small they are completely undetectable with any technology we currently possess or could realistically develop. And it does not predict a unique universe. It predicts, depending on how those extra dimensions are configured, somewhere in the neighborhood of 10 to the power of 500 different possible universes, each with different physical laws. This landscape of possibilities, as it is called, is so vast that it effectively means string theory can accommodate almost any physical reality. A theory that can explain everything explains nothing, and the scientific community is deeply divided about whether string theory is genuinely making progress or whether it has become an elaborate mathematical game that has decoupled itself from the business of actually describing the universe we live in. But perhaps the most disorienting crack in the foundation is not in cosmology, not in the fight between quantum mechanics and general relativity, but in the nature of quantum mechanics itself, in the interpretation of what quantum mechanics is actually telling us about reality. Because here is a fact that tends to get buried under the impressive accuracy of quantum predictions. After nearly a century of using this theory, physicists do not agree on what it means. They do not agree on what it is describing. They do not agree on whether it is describing an objective reality that exists independently of observation, or whether reality itself is somehow dependent on observation, or whether the question of objective reality is even scientifically meaningful. This is not a minor philosophical quibble. It is a foundational disagreement about the nature of existence, and it sits right at the heart of our most successful scientific theory. The quantum measurement problem is the name given to this deep puzzle. In quantum mechanics, a particle exists as a wave of probability, a superposition of many possible states, until a measurement is made. When measurement occurs, the wave function collapses, and the particle is found in a definite state. This is what the math says. But what does measurement mean exactly? Does it require a conscious observer? Does it require a large physical apparatus? Does it require any physical interaction at all? The original Copenhagen interpretation, developed by Bohr and Heisenberg in the early 20th century, essentially said, don't ask questions about what's happening between measurements. The mathematics works. The predictions are accurate. Accept the math and stop worrying about what it means. This was a pragmatically successful position, but it is philosophically deeply unsatisfying because it essentially removes reality from the description. It says, the only things that are real are measurement outcomes. What exists between measurements, what the particle is doing when no one is looking, is not a question physics can or should address. And if you press on that, if you ask with genuine intellectual seriousness what kind of universe it is in which things don't have definite properties until they're observed, you start walking down a very dark corridor that doesn't end anywhere comfortable. Other interpretations have been proposed, each of them stranger in its own way. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the quantum formalism completely seriously and concludes that every time a measurement occurs, every time a quantum possibility resolves into a definite outcome, all the possible outcomes actually happen. The universe branches. In one branch, the particle went left. In another, it went right. There is a version of reality where every quantum event took every possible path, where every choice you ever made spawned entire alternate universes where you made different choices. This is not metaphor. In the many worlds, interpretation, this is literal, physical truth. The universe is not a single thread of history. It is an endlessly branching tree of simultaneous realities, most of which are utterly inaccessible to us. This interpretation is mathematically consistent. It solves the measurement problem without invoking any special collapse mechanism. Some physicists, including many at the cutting edge of quantum information and quantum gravity, take it very seriously. If it is true, then the universe is not what you think it is on a scale that borders on the incomprehensible. Another interpretation, called pilot wave theory, or de Broglie-Bohm theory, attempts to restore determinism by postulating that particles always have definite positions and trajectories, guided by a real physical wave that permeates all of space. In this picture, there is no genuine randomness. The apparent randomness of quantum mechanics arises because we can never know the precise initial conditions of the particle and its guiding wave. Quantum mechanics becomes deterministic underneath. Its probabilities a reflection of our ignorance rather than genuine indeterminism in nature. This sounds appealing. It restores the classical intuition that things are what they are regardless of whether anyone is looking. But pilot wave theory comes with its own strange price. The guiding wave is non-local. It instantly connects particles across arbitrary distances. Changing something about one particle instantaneously affects the guiding wave for another particle, no matter how far apart they are. This non-locality is real, and it seems to violate the spirit, though not technically the letter, of special relativity's prohibition on faster-than-light influence. The universe, in this picture, is deeply, fundamentally entangled with itself in a way that defies conventional spatial thinking. Every particle's behavior is connected, in some non-local way, to everything else. You might think physicists could just run experiments and figure out which interpretation is correct. But here is the maddening reality. All the mainstream interpretations of quantum mechanics make exactly the same experimental predictions. They all agree on every testable outcome. The difference between them is not a difference in what they predict, it is a difference in what they describe. It is a difference in ontology, in the fundamental nature of what exists. And this means the question of which interpretation is correct is, currently, not a scientific question in the conventional sense. It cannot be resolved by experiment with our current technology and perhaps ever. We have a theory that works with extraordinary precision, and we do not know what it is describing. We are like people who have built a perfect bridge using mathematics they can't interpret. The bridge stands, the math is right, but we don't know what the math is saying about the nature of space, matter, or reality. This is not a comfortable position. For a civilization that has placed its deepest faith in science as the path to understanding. And now let us talk about time, because time is where things get truly vertiginous. You experience time as flowing. Right now, There is a past that is fixed and gone, a present moment you are inhabiting, and a future that has not yet happened. This sense of temporal flow, of time as a river carrying you forward, feels so fundamental, so primary, that it is hard to imagine questioning it. It feels like the most direct, unmediated feature of experience. You cannot step outside time. You cannot observe it from a neutral vantage point. You are always and inescapably in it. And yet physics, starting with Einstein's special relativity, has been systematically dismantling our intuitive understanding of time in ways that have radical, deeply strange implications. Special relativity established that time is not absolute. Time does not flow at the same rate for everyone. Moving clocks tick more slowly than stationary ones. This is time dilation, and it is not metaphor or approximation. It is measurably, experimentally real. Atomic clocks flown on airplanes return slightly out of sync with identical clocks left on the ground. GPS satellites require constant corrections for the time dilation caused by both their velocity and their altitude in Earth's gravitational field. Two observers moving relative to each other will disagree about whether two distant events happened simultaneously. Simultaneity, the idea that at any given moment there is a unique now that is the same for everyone, is not a feature of reality. It is a feature of your particular reference frame. The present moment that feels so vivid and singular to you is not a universal truth. It is a local perspective. General relativity deepened this strangeness. Gravity slows time. Clocks at the bottom of a mountain, closer to Earth's gravitational center, tick more slowly than clocks at the top. In the extreme, gravitational environment near a black hole, time slows toward a near-complete stop from the perspective of a distant observer. At the event horizon, the point of no return, time, to an outside observer, appears to freeze completely. The physics of space-time geometry and the physics of time are not separate things. They are the same thing. Time is not a backdrop against which events unfold. It is woven into the fabric of space, bent by mass and energy, affected by motion, fundamentally, different for different observers. None of this is theoretical conjecture. Every single one of these effects has been measured and confirmed. The universe is telling us, with great precision and complete disregard for our comfort, that time is not what we think it is. But the deepest strangeness about time comes not from relativity, but from the fundamental laws of physics more broadly, and it takes the form of a puzzle that physicists call the problem of the arrow of time. Here it is. Almost all of the fundamental laws of physics are time-symmetric. The equations of classical mechanics, quantum mechanics, and electromagnetism work equally well in both temporal directions. If you were shown a video of two billiard balls colliding and bouncing off each other, and the video was played backward, you would not be able to tell the difference. The physics is the same in both directions. The equations do not distinguish between forward and backward time, and yet you have a powerful, undeniable experience of time's directionality. Broken eggs don't reassemble themselves. Smoke doesn't flow back into a fire. Dead things don't come back to life. You remember the past, not the future. You can influence the future, not the past. There is an absolutely unambiguous arrow of time in your experience, and in the macroscopic world around you. But in the fundamental equations, in the laws that govern everything, that arrow doesn't exist. So where does it come from? The standard answer involves entropy, the measure of disorder in a system, and the second law of thermodynamics, which states that entropy always increases over time in a closed system. Things become more disordered, not less, and the arrow of time in this view is just the direction of increasing entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. This explanation works, as far as it goes, but it immediately raises a deeper question. If the laws of physics are time-symmetric, if there is no inherent direction built into the fundamental equations, then the fact that entropy increases in one direction rather than the other requires an explanation. And that explanation, when you follow it all the way back, requires that the universe began in a state of extraordinarily low entropy, that the Big Bang was, in some thermodynamic sense, an absurdly improbable state of extreme order. Why was the universe born in such a peculiar condition? This is not a question that current physics can answer. It is one of the deepest mysteries in all of science. The arrow of time, the very thing that makes your experience of life coherent and sequential, ultimately traces back to a mystery about the initial conditions of the universe that we cannot explain. And while we are sitting in that discomfort, let's push a little further, because there is a version of the time puzzle that is even more radical than what we have considered so far. Several approaches to quantum gravity and QUIC, including loop quantum gravity and certain interpretations of the Wheeler-DeWitt equation, which is the fundamental equation of quantum cosmology, suggest something that is very difficult to say without sounding like you are deliberately trying to cause philosophical distress. They suggest that time does not exist at the fundamental level, not that time is strange or relative or directionless, that it is not, in the most fundamental description of reality, a variable at all. The universe, in this view, is described by a static quantum state, a kind of timeless wave function of all possible configurations, and what we experience as time is an emergent phenomenon, an illusion generated by the way information is organized within that static state. Time, the most primary feature of your conscious experience, may not be written into the basement level of the universe. It may be something that arises, like heat from molecular motion, from the collective behavior of something that is itself fundamentally timeless. You are now, hopefully, feeling something. Not panic. This is not supposed to be a panic-inducing video, but something quieter and deeper than panic. A kind of loosening of the ground beneath the things you thought you knew. This is the correct response to this information, not because it is designed to unsettle you, but because the information genuinely is unsettling, and to fail to feel that unsettledness would be to miss something important about where we actually stand. We are not at the end of knowledge. We are not even close. We are at a peculiar and historically unprecedented moment where the tools of knowledge are sophisticated enough to reveal the scope of our own ignorance, not the ignorance of superstition or lack of measurement, but the ignorance at the heart of our most advanced and verified frameworks. The map is detailed, precise, and internally consistent in large sections. And yet the further you push into certain territories, the more clearly you can see that the map and the territory have diverged. Let's talk about information, because information has become, in recent decades, one of the most fundamental concepts in theoretical physics, and its emergence as a foundational idea has generated its own set of disturbing implications. John Wheeler, one of the most influential physicists of the 20th century, famously suggested a slogan that has become increasingly resonant: "It from bit." The idea was that at the deepest level, physical reality is not made of matter or energy or fields, but of information. What something is, at the most fundamental level, is determined by what information is encoded in it, by what answers it gives to yes, no questions posed by the universe. This sounds abstract, even mystical, but the more physics has developed in the decades since Wheeler proposed it, the more central information has become to our understanding of some of the deepest problems. Black holes, for instance, became the unlikely arena for one of the most profound debates in modern theoretical physics, a debate about whether information can truly be destroyed. In classical physics, black holes are relatively straightforward. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. Everything that falls in is gone. But in 1974, Stephen Hawking combined quantum mechanics with the physics of black holes and discovered something extraordinary. Black holes are not, in fact, perfectly black. Due to quantum effects near the event horizon, they emit a faint radiation, now called Hawking radiation, and over time, they radiate away their mass and eventually evaporate completely. This was a breathtaking result, but it came with a devastating implication. If the radiation is truly random and thermal, containing no information about what fell into the black hole, then when the black hole evaporates, all the information about whatever fell in is permanently destroyed. A star, a planet, a library full of books, a person, if any of these fell into a black hole, the information they contained would be obliterated. And this is catastrophically incompatible with quantum mechanics, which requires that information is conserved. Quantum mechanics is built on the principle that the evolution of a quantum system is reversible, that if you know the final state of a system perfectly, you can, in principle, reconstruct its past state. Information cannot simply vanish. It is one of the most inviolable principles of the theory, and yet black holes, if Hawking's calculation is correct, destroy it routinely. This conflict became known as the black hole information paradox, and for decades it was treated as an interesting theoretical puzzle. something that smart people could argue about at conferences without it affecting anyone's daily research. But over time, as the implications were examined more carefully, it became clear that this was not a peripheral curiosity. It was a symptom of the deepest possible incompatibility between the two pillars of modern physics. General relativity, which describes black holes geometrically, says that information falls in and is lost. Quantum mechanics says that information can never be lost. One of them has to be wrong, or both of them have to be wrong in ways that a deeper theory will eventually reconcile. But we don't have that deeper theory, and the more seriously physicists have engaged with the paradox, the stranger the proposed resolutions have become, until the most seriously considered possibilities have started to sound less like physics and more like science fiction, operating at the level of ontology. One of the most remarkable proposed resolutions is called black hole complementarity, developed by Leonard Susskind, Gerardus Hooft, and others in the 1990s. The idea is that an observer outside a black hole sees infalling information encoded in the Hawking radiation, scrambled and encoded but present, while an observer falling into the black hole passes through the event horizon without noticing anything special, taking the information with them. Two different observers, two different consistent descriptions of where the information is. No single observer ever sees a contradiction. This was elegant and thought-provoking, but it also introduced something philosophically alarming: the idea that reality might not be observer-independent. That too, people can have completely incompatible but equally valid descriptions of where information is, and both descriptions are physically true for their respective observers. This is not relativity of motion or relativity of time. Those are familiar now. This is relativity of fundamental facts about reality. It suggested with uncomfortable directness that the universe might not have a single, consistent, observer-independent description. And then, in 2012, a group of physicists, led by Ahmed Almheri, pushed the analysis even further and discovered that black hole complementarity itself had a fatal flaw. If you tried to make the information truly escape in the Hawking radiation, while also preserving the experience of a freely falling observer, you ran into a violation of the fundamental quantum principle called the monogamy of entanglement. Quantum entanglement, the strange correlation between particles that Einstein called spooky action at a distance, cannot be shared. If a particle outside the black hole is fully entangled with the Hawking radiation, it cannot also be fully entangled with a particle inside. But the consistency of the infalling observer's experience requires that entanglement. You can't have both. This means that at the event horizon something must break. Either the infalling observer encounters a wall of energy, what the researchers called a firewall, that destroys them instantly upon crossing, or quantum mechanics is violated, or general relativity is violated. Every path leads to a contradiction. The black hole information paradox is not solved. It has deepened into something that looks less like a problem waiting for a clever solution and more like a fundamental tear in our understanding of what physics is allowed to say. The firewall paradox, as it came to be known, sent genuine shockwaves through the theoretical physics community because it was not a vague philosophical worry. It was a precise mathematical argument showing that the combination of quantum mechanics, general relativity, and the equivalence principle, the cornerstone of general relativity, the principle that says a freely falling observer doesn't feel anything special at the event horizon, cannot all be simultaneously true. One of them has to give. And since these three ideas are the foundation of almost everything we understand about the universe, the implication is staggering. We are not just missing a piece of the puzzle. The pieces we have may be genuinely incompatible at a level that no clever adjustment will fix. Among the more remarkable responses to these problems is a conjecture that has gained serious traction in the last decade. So serious that it is now a major focus of research in quantum gravity. It is called turned EPR, coined by Juan Maldacena and Leonard Susskind, and it proposes something that would have sounded like word salad to a physicist a generation ago, that Einstein-Rosen bridges, wormholes, geometric tunnels, connecting two distant regions of spacetime, are physically equivalent to Einstein-Podolsky-Rosen pairs, which are entangled quantum particles. The conjecture says that entanglement, that mysterious quantum connection between particles that persists across arbitrary distances, might literally be the same thing as a geometric connection in spacetime. two entangled particles are not just correlated, they are connected by a microscopic wormhole. Entanglement is geometry. Geometry is entanglement. The quantum and the gravitational are not two separate things that need to be reconciled. They are two faces of the same underlying reality. If this is true, it changes everything. Not just the technical details of quantum gravity, but the conceptual framework of what space is, what connection means, what the relationship is between information and geometry. Space itself may be woven from quantum entanglement, may be an emergent structure built from the entanglement relationships between more fundamental quantum degrees of freedom. This is where theoretical physics currently lives, at the edge of ideas that are mathematically compelling and conceptually revolutionary and experimentally nearly impossible to test. The conjecture that space-time geometry emerges from quantum entanglement is not a fringe idea. It is being explored by some of the most respected theoretical physicists in the world, in some of the most prestigious institutions, and yet it remains a conjecture, a mathematical suggestion, a direction of thought rather than a confirmed theory. What it points toward is a universe in which the separation of objects in space, your left hand from your right hand, the Earth from the moon, your galaxy from its neighbor, is not a primitive fact about reality, but an emergent property of the entanglement structure of some deeper, fundamentally non-spatial quantum system. The space you inhabit, the three-dimensional stage on which your life unfolds, may not be the basement level of the universe. It may be a high-level approximation, an emergent structure that arises from something deeper, for which we do not yet have a name or a complete mathematical description. Let's step back from the frontier of theoretical physics for a moment and consider something more personal, something closer to home, something that connects the abstract strangeness of modern physics to the most immediate feature of your existence, your experience of reality. You are right now perceiving. You are taking in information through your senses, light hitting your retinas, air pressure variations registering in your cochlea, proprioceptive signals from your muscles and joints, and your brain is constructing from all of this raw data a coherent, three-dimensional, continuous experience of being in a world. You see colors, you hear sounds, you feel the weight of your own body. This experience feels direct, it feels immediate, it feels like contact with reality as it actually is. It feels like the world outside is flowing directly into your awareness, unmediated, unfiltered, transparent. And this, like so many things that feel certain, is an illusion of a quite specific and scientifically interesting kind. The colors you see are not properties of the world. They are constructions of your nervous system. The electromagnetic radiation that enters your eye has wavelength, that is its physical property. The wavelength is real, but the redness of red, the specific quality of redness as an experience, is generated by your visual cortex based on the signal from three types of cone cells in your retina. Different animals with different photoreceptor configurations experience the same wavelengths as entirely different qualities of experience. Mantis shrimp have 16 types of photoreceptors. Their color experience is presumably so rich that we cannot even imagine it. Bees see ultraviolet, snakes see infrared. The world your nervous system presents to you is not a transparent window onto physical reality. It is a species-specific, nervous system-specific, highly processed model of reality, built for survival and action, not for metaphysical accuracy. This is not a new observation. Philosophers have been making versions of this point for centuries, but it has taken on new and urgent significance in recent decades, as neuroscience has begun to reveal, in concrete physiological detail, just how much construction is happening in the act of perception. Your visual system is not passively receiving images. It is actively predicting what the world should look like based on prior experience and then checking incoming sensory data against those predictions. What you experience as seeing the world is, in large part, your brain's current best prediction, continuously updated by incoming sensory signals but shaped at every stage by expectation, prior knowledge, and top-down cognitive influence. You are not perceiving reality directly. You are perceiving your brain's model of reality. And the relationship between that model and the underlying physical world is mediated by a complex, imperfect, evolutionarily constrained nervous system that was designed to help a primate survive on the African savanna, not to accurately represent the quantum nature of space-time. The philosopher Donald Hoffman has taken this line of reasoning further than most, and his conclusion is confronting in a way that is worth sitting with. He argues, using evolutionary game theory and mathematical modeling, that evolution selects for perceptual systems that accurately represent fitness-relevant information, what helps or hurts survival, not systems that accurately represent objective reality. In simulated competitions between organisms that perceive reality accurately and organisms that perceive reality in a simplified, fitness-focused way, the fitness-focused perceivers consistently win. They are faster, more efficient, less cognitively loaded. Evolution on this account doesn't build windows onto reality. It builds interfaces, simplified, action-oriented displays that hide the underlying complexity in the service of efficient behavior. Hoffman suggests that what we perceive, three-dimensional space, solid objects, continuous time, is an interface, analogous to the desktop of a computer. The icons on a desktop don't reveal how the computer actually works. They are a simplified representation designed for a particular kind of user. And the world you see, Hoffman argues, is similarly a simplified representation, not of nothing, but of a more complex underlying reality that the interface conceals rather than reveals. If Hoffman is even partially right, the implications for science are significant in ways that are rarely acknowledged. Because science is built on observation, it is grounded in measurement and experiment, in what we can detect, what we can see, what our instruments can register. But our instruments are designed and interpreted by minds that are themselves operating with an interface, rather than a direct view of reality. Our most sensitive measurements are ultimately fed into human nervous systems for interpretation. The models we build are built by brains that evolved to track moving predators and identify ripe fruit, not to directly perceive 11-dimensional string landscapes or quantum superpositions. This doesn't make science wrong. The track record is too impressive for that, but it raises a question that is genuinely uncomfortable. What if there are aspects of physical reality that are fundamentally beyond the reach of minds like ours, not because we lack the instruments or the mathematics, but because the way minds like ours are built prevents us from even correctly formulating the questions? There is a concept in philosophy of science called the underdetermination of theory by evidence. It refers to the fact that any finite set of observations is in principle compatible with infinitely many different theoretical explanations. When scientists look at data and choose between competing theories, they use criteria like simplicity, internal consistency, and explanatory power. But these are aesthetic and pragmatic criteria, not logical necessities. The universe is not required to be simple. It is not required to use the fewest possible entities. It is not required to conform to standards of elegance or mathematical beauty, however much physicists might wish it to. And the history of physics contains many cautionary examples of theories that seemed obviously correct, that fit all available data, that were elegant and simple and internally consistent, and that turned out to be wrong. Not just incomplete, but wrong, in ways that their proponents could not have anticipated from within the conceptual frameworks they were using. Consider what happened at the end of the 19th century. Physics had achieved a state of extraordinary apparent completeness. Newtonian mechanics described the motion of everything from cannonballs to planets with precision that seemed essentially perfect. Maxwell's equations described all electromagnetic phenomena in a unified mathematical framework of breathtaking elegance. Thermodynamics explained heat, entropy, and the behavior of gases. Lord Kelvin, one of the most distinguished physicists of the age, reportedly said that all that remained to be discovered in physics was two small clouds on the horizon, a couple of minor anomalies that would no doubt soon be resolved. Those two small clouds were the failure of the Michelson-Morley experiment to detect the luminiferous ether and the ultraviolet catastrophe in the theory of blackbody radiation. Resolving them required, respectively, special relativity and quantum mechanics, the two theories that overturned essentially everything physics thought it knew about the nature of space, time, matter, and energy. The certainty of 1890 was not a reasonable assessment of where understanding stood. It was a profound and systematic failure of imagination, the inability to see from inside a conceptual framework how radically wrong that framework might be. The question that should be pressing on you now, with growing force, is whether we are in a similar position today. Whether the extraordinary precision of the Standard Model and general relativity, the remarkable success of the Lambda CDM cosmological framework, the detailed and confirmed predictions of quantum field theory, whether all of this confident, successful, experimentally verified physics might be like the Newtonian mechanics of 1890, internally consistent, extraordinarily successful within its domain, and yet ultimately resting on foundational assumptions that are wrong in ways we cannot see from where we currently stand. The pattern of history suggests we should take this possibility seriously. The depth of the current crisis, the Hubble tension, the dark sector problem, the vacuum energy catastrophe, the measurement problem, the incompatibility of quantum mechanics and general relativity, the information paradox, suggests that we should not just take it seriously, but regard it as genuinely probable. We are not in a position of minor adjustment. We may be on the edge of a conceptual revolution whose scope we cannot yet see. Now let us consider a possibility that begins in what might seem like science fiction but has, in recent years, attracted serious engagement from physicists and philosophers of science: the simulation hypothesis. The idea, most famously associated with philosopher Nick Bostrom's 2003 paper, goes like this. If civilizations can, in principle, reach a level of computational sophistication sufficient to run detailed simulations of minds and environments, and if they are inclined to run such simulations, then the number of simulated minds in existence would vastly outnumber the number of biological minds. In that scenario, pure probabilistic reasoning suggests that any given mind is far more likely to be simulated than biological. This is not an argument that we are definitely in a simulation. It is an argument that the probability cannot be dismissed without making specific assumptions about which of three possibilities is true. Civilizations never reach the computational threshold. Civilizations reaching that threshold consistently choose not to run such simulations, or we are almost certainly in a simulation. The argument doesn't tell you which horn of this trilemma is correct, but it does insist that at least one of them must be. What makes the simulation hypothesis more than a philosophical curiosity is its interaction with certain features of physics that are genuinely puzzling. The universe at the quantum level appears to be discrete rather than continuous. Energy comes in quanta. Space itself may be granular at the Planck scale. The universe appears to have a maximum speed, a maximum temperature, a maximum information density. These are features you might expect in a computational system. Systems optimized for efficiency impose limits and discretize their variables to save computational resources. None of this proves anything. The universe having a maximum speed might simply be a feature of the geometry of space-time, rather than a computational constraint. Discreteness at the Planck scale might be a property of genuine physical reality, rather than a grid resolution. But there is a strange resonance between the architecture of the universe and the architecture of a computational system, and it is difficult to dismiss entirely. Perhaps more striking is the phenomenon of quantum non-locality, the way that entangled particles, separated by vast distances, behave as if they are instantaneously correlated regardless of the space between them. John Bell proved in 1964 that this correlation cannot be explained by any local hidden variable theory, by any theory that attributes the correlations to properties the particles carried with them from their point of creation. His theorem, and the experiments that confirmed it, established that the universe is genuinely non-local in a deep sense. Things that are separated in space are connected in ways that transcend spatial separation. In a simulation, this would be trivially easy to arrange. If you are computing a world rather than physically instantiating it, there is no reason why two distant computational elements can't be instantly correlated, because distance in the simulation doesn't correspond to anything in the computational substrate running it. Again, this doesn't prove simulation, but the non-locality of quantum mechanics is one of those features of reality that is much easier to visualize in a computational context than in a physical one, and that fact, while not conclusive, is at least worth sitting with, but perhaps the most philosophically provocative aspect of the simulation. Hypothesis is what it implies about the limits of investigation from within the simulation. If we are in a simulated universe, the physics of that universe, the laws we discover through experiment and mathematics, are the laws of the simulation, not the laws of whatever is running it. We could, in principle, understand our physics completely and have no access whatsoever to the deeper physics of the substrate. The walls of our universe would be invisible not because they are hidden, but because they are the boundary of what exists from within our frame of reference. Every experiment we run, every equation we write, every observation we make would be confined to the simulation. The question of what lies beyond it would not just be empirically inaccessible, it would be logically outside the domain of inquiry available to us. We would be like characters in a novel trying to discover the laws of grammar. We could describe the world of the novel with perfect accuracy, but the substrate from which we are made, the ink and paper in the mind of the author, would be unreachable by any investigation we could conduct from within the text. Now let us move towards something that is perhaps the most vertiginous of all the territory we have crossed in this exploration, something that sits at the intersection of cosmology, philosophy, and the most fundamental questions about why anything exists at all. It is the problem of fine-tuning. The universe appears to be tuned with extraordinary precision in ways that make the existence of complex structures, galaxies, stars, planets, chemistry, life, possible. This is not a vague or impressionistic claim. It is quantitatively precise and scientifically robust. The constants of nature, the strength of gravity, the strength of the electromagnetic force, the mass of the electron, the cosmological constant, all have very specific values. And when physicists explore what would happen if these values were even slightly different, they find with disturbing consistency that even tiny variations would produce a universe radically different from ours and almost universally hostile to complexity of any kind. The cosmological constant is perhaps the most dramatic example. We already noted that it is off from its theoretically predicted value by up to 120 orders of magnitude, but the coincidence goes further than that. The observed value of the cosmological constant is small enough that it allows gravity to form structures like galaxies and stars, but large enough to be driving the accelerating expansion of the universe. If it were just a few orders of magnitude larger than it actually is, the universe would have expanded so rapidly after the Big Bang that no galaxies would have formed. If it were negative by a comparable amount, the universe would have recollapsed before stars could form. The window of values compatible with a universe like ours is extraordinarily narrow, and the cosmological constant sits, apparently by chance, within that window. Similarly, if the ratio of the electromagnetic force to gravity were different by a small factor, stars would either burn out in seconds or never ignite at all. If the mass difference between protons and neutrons were slightly different, atoms other than hydrogen would be unstable. If the strong nuclear force were a few percent weaker, protons and neutrons wouldn't bind together, and there would be no complex nuclei. No carbon, no oxygen, no chemistry. Life as we know it depends on carbon, and the production of carbon in stellar nucleosynthesis depends on a remarkable resonance in the nuclear energy levels of carbon and oxygen, a resonance predicted by Fred Hoyle before it was experimentally discovered, based on exactly this reasoning. The universe is fine-tuned for the existence of complexity, with a specificity that feels designed. There are three main responses to the fine-tuning problem, and each of them is deeply unsatisfying in its own way. The first is that there is a deeper theory we don't yet have, a theory that will explain why the constants have the values they do, deriving them from some more fundamental principle rather than treating them as arbitrary inputs. This is the hope of theoretical physicists, and it is a legitimate scientific aspiration. But we have been looking for that deeper theory for a long time, and no convincing candidate has emerged. The values of the constants appear, from within our current understanding, to be genuinely arbitrary, parameters that could have been different, that have no obvious mathematical reason to be what they are. The second response is the multiverse. If there are enormously many universes, perhaps infinitely many, each with different values of the fundamental constants, then it becomes statistically unsurprising that at least one of them has values compatible with complexity and life. We find ourselves in a universe capable of producing us because we could not exist in a universe incapable of producing us. This is called the anthropic principle, and it is formally valid as an argument, but it comes with costs. It requires committing to the existence of a vast or infinite ensemble of universes that are, by hypothesis, causally disconnected from our own, and therefore unobservable. It is not, in the conventional sense, a scientific explanation. It is a statistical argument that relies on the existence of entities we cannot detect and may never be able to detect. The third response is design, the suggestion that the constants have the values they do because the universe was intentionally configured by something or someone with the capacity to configure it. This is the domain of theology and philosophy, not physics, and it is not a scientific response. But the remarkable precision of the fine-tuning and the failure of physics to provide a satisfying natural explanation for it ensures that the question doesn't go away. The multiverse, since we have introduced it, deserves a more careful examination because it has gone from a fringe speculation to a mainstream theoretical possibility in a way that has significant consequences for how we think about science itself. There are actually several different theoretical contexts in which multiple universes arise, and they are quite distinct from one another. There is the many worlds multiverse of Everettian quantum mechanics, which we discussed earlier. There is the string theory landscape, the 10 to the power of 500 possible configurations of string theory, each corresponding to a different universe with different physics. There is the inflationary multiverse, the possibility that our universe is not the only bubble that nucleated from an inflationary expansion of space, but that the inflating space continues to produce new bubble universes endlessly, each potentially with different physical properties. And there is the cosmological multiverse of certain cyclic models, in which universes undergo repeated cycles of expansion and collapse, or in which colliding brains in extra-dimensional space produce new Big Bangs. What unites these different multiverse proposals is that they make our universe one among many, perhaps infinitely many, and they provide a potential statistical framework for explaining fine-tuning without invoking design. But what also unites them, at least in the present state of physics, is that none of them are testable in the conventional scientific sense. We cannot observe other universes. We cannot send probes into them. We cannot detect their existence by any measurement we currently know how to make. In the case of eternal inflation, some specific models predict signatures in the cosmic microwave background, regions where our bubble universe might have collided with another, leaving imprints in the primordial radiation. Searches for these signatures have been conducted and have not found convincing evidence. This doesn't rule out the multiverse. Perhaps our universe didn't collide with another, or the signatures are below the detectable threshold, or the specific inflationary model being tested is wrong while others are right. But the inability to test multiverse theories in any clean, decisive way raises a question that strikes at the heart of what science is. If a theory makes no testable predictions, if it cannot even in principle be falsified, is it science, or is it something else? Something more like metaphysics, like myth, like a story we tell ourselves because the alternative of having no explanation is too uncomfortable? Karl Popper's criterion of falsifiability, the idea that a theory is scientific if and only if it makes predictions that could in principle be proven wrong, has been central to the philosophy of science for most of the 20th century. It is a powerful and practically useful criterion, and by that criterion, the string theory landscape and the eternal inflation multiverse are not, in their current form, scientific theories. They are scientific ideas. They emerge from legitimate mathematical physics. They are taken seriously by serious physicists. They address genuine explanatory gaps. But they cannot be tested in the way that general relativity's prediction of light bending around the sun could be tested, or the way the Higgs boson could be searched for and found or not found. Some physicists respond to this by arguing that Popper's falsifiability criterion is too strict, that science has always involved unfalsifiable background assumptions, and that the predictive and explanatory power of a framework as a whole is what matters, rather than the falsifiability of each individual component. This is a legitimate philosophical point, but it represents a significant shift in what we mean by science, a shift away from the tight experimental leash that gave physics its historical authority, toward a looser standard in which mathematical elegance and theoretical coherence play a larger role. There is a physicist named Sabine Hossenfelder who has written with considerable force and clarity about what she sees as a crisis in the culture of theoretical physics. Not just a crisis of anomalous data, but a crisis of method. Her argument, developed in her book, Lost in Math, and in extensive public writings, is that theoretical physics has become seduced by beauty. Physicists have come to believe that the correct theory of nature must be mathematically beautiful. that it must be supersymmetric, that it must be elegant, that nature must exhibit specific aesthetic properties that the human mind finds appealing. These aesthetic biases have directed enormous research effort towards supersymmetry, extra dimensions, and string theory, all of which are mathematically beautiful, and none of which have produced experimentally confirmed predictions beyond what was already known. Meanwhile, less beautiful but potentially more empirically fruitful approaches have been relatively neglected. Hossenfelder is not saying the beautiful theories are wrong. She is saying that we don't know, and that our confidence that we are on the right track has been misleadingly inflated by aesthetic satisfaction rather than empirical success. Supersymmetry deserves particular attention here, because its story is both fascinating and instructive. Supersymmetry is a theoretical framework that proposes that every known particle in the Standard Model has a superpartner, a heavier particle related to it by a specific symmetry transformation. Fermions, the matter particles, have bosonic superpartners. Bosons, the force-carrying particles, have fermionic superpartners. If supersymmetry is realized in nature, it would solve several significant problems simultaneously. It would stabilize the mass of the Higgs boson against quantum corrections that would otherwise push it to enormously high values. It would provide natural dark matter candidates. The lightest supersymmetric particle, called the neutralino, would be stable and weakly interacting, making it a perfect dark matter particle. It would bring the coupling strengths of the three non-gravitational forces into closer alignment at high energies, hinting at a grand unified theory. It was, in many ways, theoretically perfect. It was so compelling that it became the dominant paradigm for physics beyond the Standard Model, directing the research programs of a generation of theoretical physicists. The Large Hadron Collider was built in part to find supersymmetric particles. It started running in 2008, reached its design energy in stages, and has now produced an enormous amount of data at the highest energies ever achieved in a collider. It discovered the Higgs boson in 2012, a triumph, but it found no supersymmetric particles, not one, despite being sensitive to superpartners across a wide range of masses that theoretical considerations suggested were the most natural and likely. The silence has been total. This doesn't definitively rule out supersymmetry. The superpartners could be heavier than the LHC can reach, or they could couple to Standard Model particles in ways that make them difficult to detect even if produced. But the most natural and most theoretically motivated versions of supersymmetry, the ones that solved the problems they were supposed to solve without introducing large fine-tuning of their own, are essentially ruled out. What remains are versions of supersymmetry that require their own fine-tuning, that solve the original fine-tuning problem by introducing a different fine-tuning problem. The elegant solution has become, in the hands of those trying to preserve it against the data, something increasingly awkward and contrived. This is the moment where you should feel the floor shifting in a particular way, not because any single experiment ruled anything out, catastrophically, but because of the pattern that is forming. Supersymmetry, for decades considered nearly certain by much of the theoretical physics community, has not appeared. Dark matter particles of the most theoretically favored types have not appeared. Extra dimensions have not been detected. String theory has not made a unique testable prediction that has been confirmed. The LHC found the Higgs boson exactly where the Standard Model predicted it would be, which was a triumph for the Standard Model but a kind of disappointment for physics beyond the Standard Model, because the Higgs's properties are almost perfectly Standard Model-like, giving no clear hints of what comes next. In field after field of high-energy physics, we have found exactly what we already knew, and nothing else. The universe is refusing to show its hand, and the theories we built, expecting that hand to be revealed, are accumulating what physicists call naturalness problems, places where numbers cancel with suspicious precision, where parameters are fine-tuned to values that seem arbitrary, where the theory works but for reasons that don't feel like understanding. There is a concept called the hierarchy problem that illustrates this naturalness issue with particular clarity. The Higgs boson has a mass of about 125 billion electron volts, a specific measured value. But quantum field theory predicts that this mass should receive enormous corrections from quantum fluctuations, corrections that would push it to a value near the Planck mass, which is about 10 to the power of 17 times larger than its observed mass. For the observed mass to be as small as it is, These corrections must cancel each other with extreme precision to about 17 decimal places. This kind of precise cancellation could happen by coincidence, but coincidences of this magnitude make theorists deeply uncomfortable because they suggest that something is going on that the theory doesn't understand. Supersymmetry was supposed to solve this by making the corrections cancel naturally, by symmetry, rather than by coincidence. Without supersymmetry, or some other mechanism we haven't found, the hierarchy problem remains, a strange, unexplained precision at the heart of the most fundamental known physics. What does it mean for a number to be unnatural? This question goes to the heart of what physicists think science is for. A number is natural, in the technical sense, if it doesn't require extreme fine-tuning to be what it is. A natural number is one that arises from the physics without cancellations of enormous quantities to many decimal places. An unnatural number is one that requires cancellations so precise that they seem like they couldn't happen by accident, that seem to require some mechanism or explanation that isn't present in the theory. The proliferation of naturalness problems in modern physics, in the cosmological constant, in the Higgs mass, in certain parameters of the Standard Model, suggests to many physicists that our current theories are missing something fundamental, that there is a deeper structure that would make these numbers natural and remove the need for suspicious cancellations. But finding that deeper structure has proven extraordinarily difficult, and the growing suspicion in some quarters is that the naturalness criterion itself, the aesthetic preference for theories without suspicious numerical coincidences, may be misleading us. Perhaps the universe simply is fine-tuned in ways that don't have deeper explanations, and our discomfort with that fact is a human psychological tendency rather than a physical insight. But if that is the case, if the universe simply is what it is, with parameters that have the values they have for no deeper reason, then physics reaches a boundary that it may not be able to cross. The dream of a theory of everything, a final unified theory that derives all physical quantities from pure, mathematical principles would fail. Not because we weren't clever enough to find it, but because it doesn't exist. The universe's constants would be brute facts, contingent and unexplained, as logically arbitrary as the particular shape of a stone by a river. This is a deeply unsatisfying conclusion, and it is not yet established. But it is a live possibility that serious physicists discuss seriously, and its very seriousness as a possibility is itself a sign of how different the current moment is from the optimistic certainties of a generation ago. Now let us circle back to something that might seem more tangible, the actual structure of space and time at the smallest scales, because here too, there are indications that our conceptual framework is breaking down in ways that go beyond technical difficulty. The Planck scale, the scale at which quantum gravitational effects become dominant, is approximately 10 to the negative 35 meters. This is so small that it makes an atom look like the observable universe in comparison. At this scale, the smooth space-time of general relativity is expected to break down completely, replaced by something whose nature we don't know. Some approaches suggest a discrete space-time foam, seething with quantum fluctuations of geometry. Others suggest that the very concept of a point in space breaks down, that space is not a collection of points but something topologically and algebraically more complex. Whatever is there, we currently have no experimental access to it. The Planck scale is so remote from anything we can directly probe that the gap between our experimental reach and the scale at which quantum gravity becomes important is, in energy terms, 15 orders of magnitude. This experimental inaccessibility is one of the deepest challenges facing fundamental physics today. The history of physics progressed by building larger accelerators to probe smaller scales, discovering new particles and forces at each step. But the energy required to probe Planck scale physics is approximately 10 to the 19th billion electron volts. The LHC operates at around 10,000 billion electron volts, roughly 15 orders of magnitude below the Planck energy. To build an accelerator that could reach Planck scale energies would, by naive extrapolation, require a machine the size of a galaxy. This is not a temporary engineering challenge. It is a fundamental practical barrier. If the physics we need to understand lies at the Planck scale, and the reconciliation of quantum mechanics and general relativity very likely requires understanding what happens there, we may never be able to directly probe it. The deepest questions about the nature of space, time, and gravity may be permanently shielded from direct experimental investigation by the immensity of the energy scales involved. Some physicists have proposed ingenious workarounds. Perhaps precision cosmology can serve as our laboratory. Perhaps the signatures of Planck scale physics are imprinted in the primordial fluctuations of the cosmic microwave background and can be read off with sufficient sensitivity. Perhaps tabletop experiments with ultra-sensitive quantum systems can reveal quantum gravitational effects in unexpected ways. Perhaps gravitational wave observations, as they mature in sensitivity and frequency range, will provide windows into regimes we couldn't otherwise access. These are legitimate hopes, and science has surprised us before with the ingenuity of indirect methods, but the gap remains enormous, and the history of the last few decades of fundamental physics, extraordinary theoretical sophistication paired with a prolonged experimental drought at the frontier, suggests that we should not assume the workarounds will be sufficient. There is something almost poetic about the situation, in a way that is more melancholy than triumphant. We have built instruments of extraordinary sensitivity, gravitational wave detectors that can measure a displacement 1/10,000th the diameter of a proton, radio telescope arrays that image the shadow of a black hole 55 million light-years away, particle detectors the size of cathedrals buried in Antarctic ice to catch neutrinos from distant supernovas. Our reach, in terms of the scales we can observe, has extended from the subnuclear to the cosmological, and what these instruments have collectively revealed is not a cleaner, simpler, more unified picture, but a more complex, more contradictory, more deeply mysterious one. Every answered question has opened 3 new unanswered ones. Every confirmed prediction has come paired with an anomaly. Every clarification has made the fog more visible rather than less. We have reached so much further than we once could, and what we have found at the edge of our reach is not resolution, but the clearer perception of how much we do not understand. Consider the cosmic microwave background, the faint glow of radiation that fills all of space, the afterglow of the Big Bang, imprinted on the sky as a nearly uniform temperature of about 2.7 Kelvin. This radiation has been mapped with extraordinary precision by successive generations of satellites, most recently by the Planck satellite, which produced a full sky map of temperature fluctuations at a resolution that represents the current state of the art in observational cosmology. The map confirms, to a remarkable degree, the predictions of the standard inflationary cosmological model, the idea that the very early universe underwent a period of exponential expansion that stretched quantum fluctuations to cosmological scales, seeding the density variations that eventually grew into galaxies and the large-scale structure of the universe. This is a genuine triumph of observational cosmology. The agreement between theory and observation is impressive, and yet, lurking in the data, there are anomalies that don't fit. Quite right. Regions where the fluctuations are too aligned, where the sky is slightly asymmetric in ways that the standard inflationary model doesn't predict, where there seems to be a cold spot that is larger and colder than the statistics of the standard model would expect. These anomalies may be statistical flukes. They may be systematic measurement effects, or they may be hints of something beyond the standard model, new physics, or a departure from the simplest inflationary scenario, or something else entirely that we don't yet have the conceptual vocabulary to name. The question of inflation itself, the framework that explains the large-scale homogeneity and flatness of the universe and predicts the spectrum of temperature fluctuations in the microwave background, has become more contested than is often acknowledged in popular accounts of cosmology. The observational evidence for the predictions of inflation is real and significant, but the theoretical status of inflation as a framework has become increasingly problematic. There are, in the space of all possible inflationary models, an enormous number of different versions, different fields, different potentials, different initial conditions, and they make a wide range of predictions. The observations constrain this space but don't uniquely pick out a specific model. More concerning, several physicists, including Paul Steinhardt, one of the original architects of inflationary theory, have argued that inflation is not the cleanly predictive framework it is often presented as. If the initial conditions for inflation can vary, and if inflation itself generically produces a multiverse of different outcomes, then the framework predicts almost any cosmological observation one might make, which is, as we noted earlier about string theory, a problem, not a virtue. And then there is the question of what drove inflation, what the inflaton field actually is. Inflation requires the existence of a field with specific properties, a potential energy that is very flat, so that the field evolves slowly and drives the exponential expansion for long enough to solve the flatness and horizon problems. No particle corresponding to the inflaton field has ever been detected. The inflaton is a theoretical necessity. Without something of this kind, the standard cosmological model doesn't work, but its physical identity is completely unknown. It might be the Higgs field, though the simplest versions of that identification don't quite work and require modifications. It might be some other scalar field not yet discovered. It might be something more exotic. The uncertainty about the physical identity of the inflaton means that inflation, for all its observational success, is built on an unknown foundation. The engine that drove the first fraction of a second of the universe's history, shaping everything that followed, is something we cannot identify. What emerges from all of this, from the Hubble, tension, the dark sector, the incompatibility of quantum mechanics and general relativity, the information paradox, the measurement problem, the fine-tuning puzzle, the failure of supersymmetry, the experimental inaccessibility of the Planck scale, the anomalies in the microwave background, the unknown nature of inflation, is not a collection of isolated puzzles waiting to be solved one by one. It is a portrait of a crisis that is systemic. The cracks are not in the walls of physics. They are in the foundation. And the remarkable thing, and the thing that distinguishes this moment from earlier moments of scientific difficulty, is that the crisis is not hidden. It is not being suppressed or denied by the scientific community. The physicists who work in these fields are, by and large, acutely aware of how deep the problems run. They discuss them openly. They argue about them at conferences. They publish papers acknowledging that the standard models are inadequate and that new frameworks are urgently needed. The crisis is real, it is acknowledged, and it is unresolved. There is a concept that physicists sometimes use to describe the situation of a theory that works extraordinarily well within its domain, but is known to be fundamentally incomplete. They call it an effective field theory. An effective field theory is one that gives accurate predictions within a certain range of energies or scales, but that explicitly acknowledges its own limitations and breaks down at energies or scales beyond its domain of validity. It is, in a sense, a theory that knows it doesn't know everything. The standard model of particle physics and general relativity are both, in this sense, effective field theories. They work with extraordinary accuracy within their respective domains, but each one breaks down somewhere. The standard model at energies near the Planck scale, general relativity at singularities and at the quantum level. An effective field theory is not wrong. It is a precisely characterized approximation. But the word approximation should give you pause, because when we ask what the universe actually is, an approximation, however precise, is not an answer. What would a genuine revolution in physics look like? Not an incremental expansion of what we know, but the kind of conceptual restructuring that happened when Newton's absolute space and time gave way to Einstein's dynamic space-time, or when the certainties of classical determinism gave way to quantum probability. It would not look, from the inside, like progress in the conventional sense. It would look like the discovery that some question we thought we had answered was actually being asked wrongly. It would require abandoning not just specific theories, but the conceptual categories in which those theories were formulated. Einstein didn't just add corrections to Newtonian mechanics. He showed that the very concepts of absolute space and time were the wrong categories to use. The next revolution, whatever form it takes, will likely require something similar. The recognition that some category we are currently using to describe the universe is not a feature of reality, but an artifact of our limited perspective. What might those wrong categories be? Several candidates have been suggested by physicists working at the frontier. Space and time themselves might be wrong categories, emergent approximations rather than fundamental features of reality, arising from some deeper quantum, informational structure. This is the direction pointed to by the EPR conjecture and by the broader research program of it from qubit, the idea that space-time geometry emerges from patterns of quantum entanglement. If this is right, then asking, what happened before the Big Bang, or what is inside a black hole, are questions that use concepts, before, inside, spatial location, that don't apply at the level where the answer lives. They are questions asked in the wrong language and No amount of cleverness in the current language will produce a correct answer. You would need to translate into the language of quantum information, and then retranslate the answer back, if such a translation is even possible. Causality might be a wrong category. The notion that causes precede effects, that there is a definite causal structure to events, that the direction of influence flows from past to future. These are features of our experience, and they are reflected in the mathematical structure of physical theories. But there are approaches to quantum gravity that suggest causal structure is itself emergent, that at the most fundamental level there is no definite causal ordering of events. One approach, called causal dynamical triangulations, attempts to derive space-time geometry by summing over all possible causal structures, allowing the geometry to emerge dynamically. Another, developed by Raphael Sorkin and collaborators, proposes that the fundamental structure of space-time is a causal set, a discrete, partially ordered set of events in which the ordering relation is the only fundamental geometric datum. In these approaches, the smooth, continuously causal space-time of everyday experience and classical physics is an approximation that emerges from a much more complex underlying structure, in which causality, as we usually think of it, is not a primitive feature. The concept of a particle, one of the most fundamental categories in all of physics, the idea that matter is made of discrete, countable entities, might itself be a wrong category in certain contexts. Quantum field theory already begins to dissolve this concept. In quantum field theory, what we call a particle is not a permanent thing, but an excitation of a quantum field, a ripple in an underlying field that pervades all of space. The photons that carry light are excitations of the electromagnetic field. The electron is an excitation of the electron field. And crucially, the concept of a particle is observer-dependent in quantum field theory. Depending on the state of motion of the observer, the same quantum state of a field can look like a vacuum, no particles, or like a thermal bath of particles. This is the Unruh effect, predicted by physicist William Unruh in 1976. An observer undergoing constant acceleration sees the vacuum of an inertial observer as a warm gas of particles. The particles aren't there for the inertial observer and are there for the accelerating observer. What is or isn't a particle depends on who's asking. If particles are observer-dependent in this way, then matter, the stuff the universe is made of, is not as objective as it seems. It is, in part, a relational concept, defined not just by what is out there, but by the relationship between what is out there and the observer. The observer. Here we arrive at something that cannot be avoided any longer. Something that quantum mechanics has been pointing at since the beginning and that physicists have been arguing about ever since. What is the role of the observer in physics? In classical physics, the observer is irrelevant. The universe does what it does regardless of whether anyone is watching. The act of observation is passive. The observer detects what is happening without disturbing it in any fundamental way. But in quantum mechanics, the act of observation is not passive. It is, in the standard formulation, the moment at which the wave function collapses, the moment at which the superposition of possibilities resolves into a definite outcome. The observer doesn't just detect reality. In some sense, that is still being actively debated. The observer participates in bringing a definite reality into being. This participation of the observer is one of the deepest unresolved issues in the foundations of physics, and it connects, in ways that are simultaneously exciting and troubling, to questions about consciousness, about the nature of the mind, and about the relationship between the physical world and subjective experience. Some physicists, including Eugene Wigner and John Wheeler, took seriously the possibility that consciousness plays a special role in quantum mechanics, that the collapse of the wave function requires not just a physical measuring device but a conscious observation. This view, sometimes called the consciousness causes collapse interpretation, is considered fringe by most physicists today, but it has never been definitively refuted, and in a period when every other interpretation of quantum mechanics has its own serious problems, even fringe ideas deserve honest consideration. More recently, theories of quantum consciousness, most notably the Penrose-Hameroff theory that consciousness arises from quantum computations in microtubules within neurons, have proposed that the mind and the quantum world are entangled in ways that go beyond simple metaphor. But you don't need to commit to consciousness collapse theories to feel the deep strangeness here. Even in the most conservative interpretations of quantum mechanics, the act of measurement plays a special role that has no classical analog. Even if you hold that the observer is just a large physical system whose interaction with a quantum system causes decoherence, the loss of quantum superposition into classical-looking probabilities, you are still left with a picture of the world in which what we see is systematically different from what is there when we are not looking. Decoherence explains why superpositions seem to disappear at the macroscopic level. It is not that the superposition collapses, but that the quantum coherence between different parts of the superposition leaks into the environment, making the different branches effectively invisible to each other. But decoherence on its own doesn't explain why we see definite outcomes, rather than a superposition of all possible outcomes. It explains why the branches don't interfere with each other, but not why we find ourselves in one branch rather than seeing all of them simultaneously. The question of why observation produces a single, definite result remains unanswered. This question connects to the hard problem of consciousness, the question of why there is subjective experience at all, why there is something it is like to be you, why the physical processes in your brain produce not just information processing, but the felt quality of awareness, the redness of red, the painfulness of pain, the sense of being here now as a specific experiencing subject. The hard problem is, if anything, even more resistant to scientific explanation than the measurement problem in quantum mechanics. Neuroscience has made extraordinary progress in correlating brain states with mental states, in identifying the neural correlates of specific experiences, in understanding the information processing mechanisms underlying perception and cognition. But the question of why any of this information processing is accompanied by subjective experience, rather than happening in the dark without any felt quality, is completely untouched by these discoveries. The correlation between brain activity and experience is well established. The explanation of why physical processes produce experience at all remains completely absent. Some philosophers and physicists have responded to this by proposing that consciousness is not a product of complex physical processes but a fundamental feature of reality, that it is as basic as mass or charge, present to some degree in all physical systems, and that what we call consciousness in humans is a particularly complex form of something far more widespread. This view is called panpsychism, and in various forms it has been advocated by philosophers like David Chalmers and Philip Goff, and with some mathematical elaboration by Giulio Tononi through his integrated information theory. Panpsychism is not a mainstream scientific position, but it is a serious philosophical one, and the fact that it is being taken seriously by rigorous thinkers is itself a reflection of how deeply problematic the alternatives are. Materialism, the view that consciousness is entirely reducible to physical processes, cannot currently explain why those processes produce experience. Dualism, the view that mind and matter are fundamentally different substances, faces its own notorious difficulties in explaining how they interact. Neither standard materialist nor standard dualist accounts have solved the hard problem, and panpsychism, despite its apparent strangeness, avoids the hard problem by refusing to derive consciousness from non-consciousness in the first place. If consciousness is fundamental, if experience in some form is woven into the fabric of reality at the deepest level, then the picture of the universe that physics has been building for 3 centuries is not wrong exactly, but profoundly incomplete in a particular direction. The universe would not be a collection of unconscious matter and energy from which minds accidentally emerged through the complexity of biological evolution. It would be, in some sense, a universe in which mind and matter are aspects of a single underlying reality, neither reducible to the other, both equally fundamental. This is not a conclusion that emerges from conventional physics, but the failure of conventional physics and neuroscience to solve the hard problem of consciousness is itself a datum that deserves weight. The most successful scientific civilization in the history of life on Earth cannot explain why it is conscious. That is an extraordinary fact, and it should inform how confident we are in the completeness of our current picture. Let us take a step back and look at the situation from a broader perspective, because there is something important to be said about the cumulative arc of what we have covered, and about what it implies. For the project of understanding the universe, we have seen that the cosmological standard model has serious anomalies that resist resolution. We have seen that the particle physics standard model is missing 95% of the universe's content. We have seen that quantum mechanics and general relativity are incompatible, and that resolving their incompatibility has proven extraordinarily difficult. We have seen that quantum mechanics itself, despite its empirical success, lacks an agreed-upon interpretation and raises fundamental questions about the nature of reality, observation, and information. We have seen that time, space, particles, and causality, the basic categories of physical description, may themselves be emergent approximations rather than fundamental features of the world. We have seen that consciousness, the most immediate fact of our existence, remains unexplained by physics or neuroscience, and we have seen that the fine-tuning of the universe's constants raises deep questions about why the universe is the way it is that current physics cannot answer. Each of these problems, taken alone, might be described as a challenge waiting to be solved, a gap in an otherwise solid edifice of understanding. But taken together, they suggest something different. They suggest that the picture of reality we have built is not a nearly complete structure awaiting a few final pieces. It is a partial map of a territory whose extent and nature we are only beginning to appreciate. And the most unsettling possibility, the one that increasingly thoughtful physicists are beginning to take seriously, is that the incompleteness is not accidental, that the problems are connected, that they are different facets of a single, deep, as yet unnamed failure of understanding that cuts across all of our current frameworks and will require something as radical as the invention of quantum mechanics, or more radical, to resolve. What would it feel like to be inside that kind of revolution in the years before it happened? It would feel exactly like this. It would feel like accumulating anomalies that refuse to go away. It would feel like increasingly elaborate attempts to preserve the existing framework against the data, adding epicycles, adjusting parameters, invoking new entities like dark matter and dark energy that are defined primarily by what they are not. It would feel like a growing tension between the precision of established theory in its domain and the failure to extend that theory beyond its domain. It would feel like a proliferation of competing speculative frameworks, none of which commands overwhelming support, and none of which has made the decisive experimental prediction that would force a consensus. It would feel like the increasing irrelevance of the criterion that made science great, direct experimental test, in the domains where the deepest questions live. It would feel exactly like the current moment in physics. The people inside the pre-quantum, pre-relativistic physics of 1890 could not have predicted what the resolution would look like. They could identify the anomalies, the Michelson-Morley result, the ultraviolet catastrophe, but the resolution required conceptual tools that didn't yet exist. It required abandoning the concept of absolute simultaneity, a concept so embedded in intuition that even after Einstein showed it was wrong, many physicists resisted for years. It required embracing quantization, the idea that energy comes in discrete lumps, which had no precedent in classical physics and seemed to minds trained in the continuous mathematics of classical mechanics deeply unnatural. The revolution was not just a new answer to an old question, it was a reconceptualization of what the questions were, and this is where we are now, in a deeper sense than even the technical details suggest. The questions that we are asking, the questions that physics is failing to answer. What is dark matter? What is dark energy? How do quantum mechanics and gravity unify? What happened at the Big Bang? What is the correct interpretation of quantum mechanics? These may not be the right questions, or rather, they may be the right questions phrased in the wrong language, using conceptual categories that the eventual understanding will show to have been naive. Just as "what is the luminiferous ether made of?" was eventually recognized as a question based on a false premise. Some of our current questions may be waiting to be dissolved rather than answered. What would dissolving these questions require? It would require, in the first instance, the recognition of where our current conceptual frameworks are generating the confusion. This is always the hardest part, because we tend to mistake the framework for reality itself. We don't notice the assumptions that are so deep they seem like facts about the world, rather than choices about how to describe it. The assumption that space is a container rather than a relational structure. The assumption that time flows rather than being a static dimension of a four-dimensional block. The assumption that observers are passive detectors of a pre-existing reality. the assumption that the laws of physics are universal truths rather than effective descriptions valid within a particular domain. These assumptions are not obviously wrong. They are baked into our most successful theories. But the history of physics suggests that at every revolutionary moment, some deeply baked-in assumption turned out to be the source of the impasse, and releasing it was what allowed the next framework to form. There is a particular thought experiment that John Wheeler used to like to pose, and it captures something important about the moment we are in. He called it the game of 20 questions, variant. In the original game, one player thinks of an object, and the others try to identify it by asking yes or no questions. In Wheeler's variant, there is no predetermined object. Each player who answers a question can answer however they like, as long as they are consistent with all previous answers. By the time 20 questions have been asked, an object has been conjured from the interactions, not from a prior fixed reality, but from the process of questioning and answering itself. Wheeler used this as a metaphor for quantum mechanics and for the universe more broadly. Reality, he suggested, is not a pre-existing structure waiting to be discovered. It is, in some deep sense, brought into being by the process of inquiry, by the questions we ask, and the measurements we make. The universe, he wrote, does not exist out there, independent of us. We are inescapably involved in bringing about that which appears to be happening. Whether Wheeler was right about this in a literal, physical sense is something that cannot currently be settled, but the spirit of his suggestion points at something that is genuinely important, regardless of the answer. The questions we ask shape what we find. The categories we use to think with determine what kinds of understanding are accessible to us. The instruments we build and the measurements we design reflect choices about what we consider worth measuring. And a civilization that has spent 3 centuries developing an extraordinarily powerful, but ultimately partial framework for describing reality is, in a very real sense, constrained by the success of that framework in ways it may not be able to see from within. Let us speak for a moment about the universe's age and scale, because sometimes returning to the sheer numbers helps put the intellectual situation in perspective. The observable universe is approximately 93 billion light-years across. It contains something on the order of 2 trillion galaxies, each containing hundreds of billions of stars, many of those stars orbited by planets, many of those planets in conditions that might, in principle, support chemistry complex enough to generate the kind of informational organization we call life. The universe is approximately 13.8 billion years old. The Sun is about 4.6 billion years old. Complex, multicellular life on Earth has existed for perhaps 600 million years. Homo sapiens, our species, has existed for perhaps 300,000 years. Recorded history spans perhaps 5,000 years. Modern science in any recognizable form is perhaps 400 years old, the period in which we have had the theoretical and experimental tools to probe the deep structure of reality, quantum mechanics, relativity, particle accelerators, radio telescopes, is less than 100 years old. We are 100 years into a project of understanding a 13.8 billion-year-old universe of incomprehensible scale and complexity, using instruments and conceptual frameworks that were developed in the blink of a cosmic eye by a species that spent most of its evolutionary history worrying about food and predators rather than the quantum structure of space-time. The wonder is not that we don't understand everything. The wonder is that we understand as much as we do. But the confidence with which we have sometimes spoken, the suggestion that a theory of everything was within reach, that the fundamental laws of nature were nearly in hand, that confidence was, in the light of our actual situation, a form of hubris that the universe is now quietly and methodically correcting. When you look up at the night sky, and there are fewer and fewer places on Earth where you can still see the Milky Way clearly, which is itself a peculiar kind of tragedy. You are looking at light that left its sources years, decades, centuries, millennia ago. The star you are looking at may no longer exist. The light that enters your eye is a message from the past, transmitted across space at the universe's speed limit, received by a biological instrument tuned to a specific narrow band of the electromagnetic spectrum, interpreted by a brain that constructs from it a simplified model of what is out there. The sky you see is not the universe as it is. It is the universe as it was, filtered through the capabilities and limitations of your sensory system, translated into a conscious experience whose relationship to the underlying physical reality is profoundly mediated and partial. And yet something remarkable happens in that translation. You feel the enormity. You feel, however imperfectly, the scale and the age and the strangeness of what you are looking at. Your brain, which evolved to navigate social hierarchies and track prey across savanna, is somehow capable of grasping, at least partially, at least emotionally, that those points of light are entire stellar systems, entire galaxies, remnants of events billions of years in the past, components of a structure whose full extent is beyond visualization. The capacity for awe is one of the genuinely extraordinary things about the kind of mind your species developed, and it matters here, not as a sentimental consolation but as a genuine epistemic signal. Awe is what you feel when you encounter something whose scale or strangeness or depth exceeds your capacity for ordinary comprehension, and the universe, the more honestly you look at it, generates awe not because it conforms to beautiful equations, but because it persistently and dramatically exceeds them. The physics of the last century has given us something genuinely breathtaking. It has extended the reach of human understanding in every direction, to the smallest scales, to the largest structures, to the earliest moments of cosmic time, to the most extreme physical conditions. The standard model of particle physics is a permanent achievement of the human mind, as real and as durable as anything the species has produced. General relativity is one of the most beautiful and profound scientific theories ever written. The discovery of quantum mechanics fundamentally and permanently changed our understanding of what nature is at the microscopic level. These are not errors waiting to be erased. They are accurate and important descriptions of significant aspects of reality. When the deeper framework comes, whatever it is, it will not erase these descriptions. It will contain them as approximations, valid within their domains, the way general relativity contains Newtonian mechanics as a limiting case. But the deeper framework has not come, and the absence of the deeper framework, after decades of extraordinary effort by extremely talented people, is itself telling us something. Not that the effort has been wrong, not that the tools are inadequate, but that the problem is harder than we thought. Harder in a way that may require not just new mathematics or new experiments, but new ways of thinking that are difficult to achieve from within the assumptions we currently hold. There is a beautiful and sobering quote attributed to Einstein, who said that we cannot solve our problems with the same thinking we used when we created them. He was talking about political problems, but the remark applies with equal force to physics. The conceptual framework that gave us quantum mechanics and general relativity is the same framework that is now telling us those theories are incompatible and incomplete. To go beyond the incompleteness, we may need to go beyond the framework. Going beyond the framework is the hardest thing in intellectual life. It requires the ability to see your own assumptions from the outside, to hold your categories lightly rather than treating them as the structure of reality itself. It requires a kind of intellectual courage that is different from and rarer than the courage to follow a mathematical argument wherever it leads. It requires being willing to feel lost, to work without the guidance of a clear paradigm, to explore in directions that may not resolve into anything clean. Several physicists are doing exactly this, in ways that are not always visible in popular accounts of the field. There are researchers working on approaches to quantum gravity that abandon the concept of a fixed background spacetime from the beginning. There are physicists building frameworks in which the fundamental objects are not particles or fields or strings, but information-theoretic structures, graphs, networks, simplicial complexes, whose large-scale behavior produces the appearance of space-time. There are people working on reconstructions of quantum mechanics trying to derive it from more fundamental informational principles rather than accepting its standard axioms as given. There are cosmologists developing models of the universe that don't begin with the Big Bang, that treat time as cyclic or bouncing or emerging from a deeper pre-geometric state. None of these programs has yet produced the decisive breakthrough, but the activity itself, the willingness to question everything, to abandon comfortable assumptions and work in the cold wind of genuine uncertainty, is exactly what a genuine revolution looks like in its early stages. And while we are sitting in that cold wind, let us consider one more layer of the problem, one that is rarely discussed in popular science, But that is, in the opinion of a growing number of physicists and philosophers, potentially the deepest of all. It is the question of whether mathematics is discovered or invented, whether the mathematical structures that describe the physical world are features of an objective, mind-independent mathematical reality, a Platonic realm of pure structure, or whether they are inventions of the human mind, tools we have developed for manipulating certain kinds of information, tools that happen to be extremely useful for describing patterns in the physical world, but that have no deeper metaphysical status. This question might seem academic, but it has direct bearing on what we can expect from physics and how we should interpret the remarkable success of mathematics in describing the natural world. Eugene Wegner, in a famous 1960 essay, called the success of mathematics in natural science unreasonably effective. He noted that mathematical structures developed by pure mathematicians, with no applications in mind, driven purely by aesthetic and logical considerations, have repeatedly turned out to be exactly the right tools for describing physical reality. Non-Euclidean geometry, developed in the 19th century as a pure, mathematical exploration, turned out to be the language of general relativity. Group theory, developed as abstract algebra, turned out to be the language of particle physics. Complex Hilbert spaces, developed as pure mathematics, turned out to be the language of quantum mechanics. This unreasonable effectiveness is genuinely puzzling, and it points in one of two directions. Either the universe is, at some deep level, mathematical. It is made of mathematical structure rather than described by it. Or human minds and the physical universe are both products of some common process that makes them resonant with each other in ways we don't fully understand. Max Tegmark has pursued the first possibility with full seriousness, proposing what he calls the mathematical universe hypothesis. The idea that our physical universe is not just described by mathematics, but is a mathematical structure. In this view, there is no distinction between the map and the territory. The territory is the map. Physical reality is not something that instantiates mathematical relationships. It is those relationships, as real and as abstract as any mathematical object. This is a radical position, and it has implications that are as strange as any we have encountered. If every mathematical structure is real, if every self-consistent mathematical system is a universe, then we live in one of an inconceivably vast landscape of mathematical realities, and our universe is distinguished from the others only by the fact that it contains observers capable of asking what kind of universe they live in. This is, in its own way, a version of the anthropic argument, pushed to the most extreme possible limit, and it has the same virtue and the same vice as the multiverse. It potentially explains fine-tuning by removing the need for a special explanation, while doing so at the cost of postulating an infinity of unobservable realities. What all of these ideas, the multiverse, the simulation hypothesis, the mathematical universe hypothesis, the emergence of space-time from quantum entanglement, the fundamental role of information, the possible primacy of consciousness, have in common is that they are attempts to answer a question that physics has traditionally refused to ask. Not, how does the universe work, but why is there a universe at all? Not, what are the laws of nature, but why are there laws of nature, and why are they these particular laws? These are questions that sit on the boundary between physics, philosophy, and something that doesn't yet have a name. And the fact that serious physicists are engaging with them now, using the tools of mathematics and information theory and quantum gravity, is not a sign that physics has lost its way. It is a sign that physics has reached a frontier where the traditional methods are insufficient, and the deepest questions can no longer be avoided by looking the other way. There is a thought that has been forming throughout this entire exploration, a thought that I want to name directly now because it connects everything we have discussed and points towards something that is simultaneously disturbing and exhilarating. The thought is this: we may be approaching the limits of what minds like ours can understand, not the limits of what is in principle knowable, not the limits imposed by practical experimental constraints, but the limits imposed by the cognitive architecture of the kind of intelligence that evolved on this planet. The universe may be deeper than human thought can penetrate, not because there is nothing deeper to penetrate, but because the instruments we use for penetration, our minds, our mathematics, our intuitions about space and time and causality, were not built for that depth. This is a difficult thought to sit with because it threatens to make the search meaningless. Why explore the universe if the exploration has a ceiling built into the nature of the explorer? But this would be the wrong conclusion. The history of science shows that even within the constraints of human cognition, we can extend our reach far beyond what seemed possible by building instruments that amplify our senses, by developing mathematics that encodes relationships our intuition cannot directly grasp, by building conceptual frameworks that allow us to reason carefully about things we cannot directly experience. We reached quantum mechanics, which is profoundly counterintuitive, by following mathematics and experiment even when they led away from comfortable intuition. We reached general relativity by following the logic of a principle, the equivalence of inertial and gravitational mass, to its geometric conclusion. We can, in principle, push further in the same way, but pushing further may require acknowledging more explicitly than we usually do the gap between our models and reality, the provisional status of our most fundamental concepts, the possibility that the universe does not owe us an explanation in terms we find intuitive or even comprehensible. Science works by the construction of models, by the building of approximate, partial, testable representations of aspects of reality. It does not work by the direct apprehension of truth. The models we build are extraordinary achievements, and they allow us to do things that would seem magical to our ancestors. But they are models. They are not the thing itself, and the accumulated evidence of the last several decades of fundamental physics is that the model we currently have, as successful as it is within its domain, is not adequate to the full depth of what the universe appears to be. There is a specific kind of intellectual vertigo that comes from following this line of thought to its natural conclusion, and it is worth allowing yourself to feel it, rather than retreating from it into the safety of familiar certainties. You are a biological organism on a small rocky planet, orbiting an unremarkable star in the outer regions of one galaxy among 2 trillion. Your brain, the instrument you are using right now to process this information, is an electrochemical network of approximately 86 billion neurons, connected by something like 100 trillion synapses, operating on principles that evolution refined over hundreds of millions of years for purposes that had nothing to do with understanding quantum gravity. The reality you experience is a model generated by that brain, a model that is useful, coherent, and deeply convincing, but that is demonstrably incomplete and demonstrably shaped by the particular history and architecture of the system generating it. And when you use that brain to do physics, to write equations, to design experiments, to interpret data, you are using the model to study the thing that generates the model, which is a situation that epistemologists call deeply circular, and which may impose limits on what conclusions the investigation can reach. This, circularity is not a reason to stop doing science. It is a reason to hold scientific conclusions, particularly the most fundamental ones, with a specific kind of humility, a humility that acknowledges the tools being used, that remains open to the possibility that the tools themselves may be distorting the picture in ways that are difficult or impossible to detect from within. The greatest scientists have always had this quality. Einstein questioned the assumption of absolute simultaneity that everyone else took for granted. Bohr questioned the assumption that physical quantities have definite values independent of measurement. Wheeler questioned the assumption that the universe exists independently of observation. These were not just technical adjustments. They were moments of genuine epistemic courage, moments when a thinker looked at a fundamental assumption that their entire framework rested on and said, quietly and with full awareness of the consequences, "What if this is wrong?" We are at a moment that calls for exactly that kind of courage, applied to whatever the relevant fundamental assumptions of our current framework turn out to be. We don't yet know which assumptions those are. That is precisely what makes the moment both difficult and exciting. It is the moment before the revolution, when the anomalies are visible but the new framework has not yet formed, when the old answers are clearly insufficient but the new questions have not yet been correctly posed. This is an uncomfortable place to be. Human psychology prefers resolution. It prefers the clean narrative of discovery, the moment when the puzzle is solved and the picture becomes clear. But the universe does not care about our preference for resolution, and the history of science suggests that the most important moments are precisely the ones before resolution, the ones of productive confusion, of multiplying contradictions, of frameworks straining against data they cannot accommodate. Let us think for a moment about what we know about the universe's beginning. because the origin of everything is perhaps the place where our ignorance is most stark and most consequential. The standard cosmological model tells us that approximately 13.8 billion years ago, the observable universe was compressed into a state of extreme density and temperature, and that from this state it expanded and cooled, producing in sequence the fundamental particles, then light nuclei, then atoms, then the first stars and galaxies, then the complex chemistry that eventually produced life, then you. This narrative is supported by an impressive array of evidence: the cosmic microwave background, the relative abundances of light elements, the recession of galaxies, the large-scale structure of the universe. It is a remarkable scientific achievement, but it has a boundary, and at that boundary, it stops completely. The boundary is approximately 10 to the negative 43 seconds after the Big Bang, the Planck time. Before that moment, or rather at that moment and earlier, the conditions of density and curvature are such that quantum gravitational effects dominate and our current theories break down entirely. We cannot say what happened at the Big Bang. We cannot say what, if anything, existed before it. We cannot say whether before is even a meaningful concept in that context, since time itself may have emerged from the Big Bang rather than pre-existing it. We cannot say whether the Big Bang was a beginning in any absolute sense, or whether it was a transition from some earlier state, a bounce from a previous contracting phase, a tunneling event from a pre-geometric quantum state, a collision of higher dimensional membranes. All of these are speculative possibilities with varying degrees of theoretical motivation, and none with direct observational support. The question of what happened at and before the Big Bang is not just unanswered. It is, with current tools, unanswerable. And the question of why there is a universe at all, why there is something rather than nothing, sits even further beyond the reach of current physics. This is, in a sense, the ultimate question, and it is one that science in its current form cannot address. Some physicists, like Lawrence Krauss, have argued that quantum mechanics provides an answer, that the universe could arise from nothing through quantum fluctuations, that the laws of quantum mechanics allow for the spontaneous creation of something from an initial state of nothing. But philosophers have pointed out, correctly, that this is not really an answer to the question as traditionally posed, because the quantum mechanical framework from which the universe arises is itself something. It contains laws, mathematical structures, the possibility of fluctuations. The question, why is there something rather than nothing, is asking why there are laws at all, why there is a mathematical structure at all, why existence itself rather than pure absolute non-existence. And to that question, no scientific or philosophical answer has yet been given that commands widespread agreement or genuine explanatory force. David Deutsch, the physicist and philosopher, has argued that explanatory understanding, deep, genuinely illuminating explanation of why things are the way they are, is always in principle reachable, that there is no hard ceiling on what good explanations can achieve. He calls this the principle of optimism about knowledge, and it is an inspiring vision. But even Deutsch acknowledges that the explanations we reach may look very different from the ones we expect, may require the abandonment of current categories, and the development of new conceptual frameworks whose nature we cannot anticipate in advance. The optimism is not the optimism of a clear path to a known destination. It is the optimism of confidence that the journey has no absolute limit, even if the destination is not visible and the terrain is more complex and strange than any map we currently hold. There is something worth saying about the emotional texture of this situation, about what it is like, or what it should be like, to genuinely inhabit the uncertainty that we have been exploring. Popular science has a tendency to present mystery as a temporary inconvenience, an interesting puzzle whose solution is just around the corner, a source of excitement that will be resolved into satisfaction in due course. And sometimes that is true, but sometimes, and this seems to be one of those times, the mystery is deeper than that. The current situation in fundamental physics is not like a detective novel where the clues are all there and the solution is waiting to be deduced. It is more like opening a door to find that the room behind it is larger than the building, that the space you have entered has properties that violate the geometry of the space you entered it from, that the tools you brought to solve the puzzle are the wrong tools for the kind of puzzle it turns out to be. The response to that kind of situation is not panic, and it is not dismissal. It is a kind of patient, alert, open-ended attention that holds the contradiction, rather than resolving it prematurely. The Zen tradition has a concept for this: don't know mind, the capacity to rest in genuine not knowing without collapsing into either forced certainty or paralysis. Science at its best has this quality. The best scientists are those who can follow the evidence into unfamiliar territory without losing their nerve, who can maintain the discipline of empirical rigor while allowing their conceptual frameworks to become genuinely fluid. The moment we are in requires exactly this from physics and from the people who try to understand physics from the outside. It is worth noting, in this context, that the history of science's greatest breakthroughs has consistently been characterized by a refusal to accept the existing explanation as final, even when the existing explanation was working extremely well. Newton's mechanics worked perfectly for 2 centuries before anyone had the evidence to question it seriously. But the questioning, when it came, did not wait for the evidence to be overwhelming. Einstein was driven by a theoretical discomfort, a sense that the symmetries of Maxwell's equations and the structure of Newtonian mechanics were inconsistent in a way that demanded resolution. Planck introduced the quantum hypothesis reluctantly, not because he believed it was true, but because it was the only way to make the mathematics of blackbody radiation work. The evidence for the existing framework was not what prevented the revolution. The revolution came from people who, despite the evidence for the existing framework, sensed that something was wrong at a deeper level and followed that intuition into territory that had no map. Today, there are physicists who carry a similar intuition, that something is wrong at a level deeper than the current anomalies reveal, that the crisis we can measure is the visible surface of a deeper crisis we haven't yet found the right language to describe. They are not always the most prominent voices in the field. The most prominent voices are often those defending and extending the existing frameworks, because the existing frameworks are where the funding is, where the careers are built, where the accumulated institutional authority of the field resides. But the intuition that something fundamental is missing is widespread, even among those who defend the existing frameworks in their daily work. It surfaces in conversations, in the unguarded moments of conference talks, in the footnotes of papers where physicists acknowledge, in careful language, that they don't really know what their equations mean at the deepest level. There is something that needs to be said about the relationship between this intellectual situation and the way it is communicated to the public, because there is a significant gap between how the crisis in fundamental physics is experienced by physicists and how it is presented in popular science. Popular science tends to emphasize the triumphs, the confirmed predictions, the new discoveries, the progress narrative. It is more comfortable, more inspiring, more fundable. The anomalies get mentioned briefly, as interesting puzzles. The depth of the theoretical crisis is rarely conveyed. The extent to which the foundational frameworks are in genuine conflict, the degree to which the most fundamental questions remain unanswered, the possibility that our current paradigm is as wrong, in its own way, as the pre-quantum paradigm of 1890. These things are usually softened, qualified, or omitted in the interest of a narrative that the public can receive without alarm. This is understandable, but it is ultimately a disservice, both to the public and to science itself. The public's confidence in science should be grounded not in the false impression that physics has it essentially figured out, but in an accurate understanding of how science actually works, including the crucial role of crisis, of revision, of the willingness to be wrong. Because science's greatest strength is not that it is right, it is that it has a method for finding out when it is wrong. The experimental method, the peer review process, the culture of skepticism and verification, the requirement that theories make testable predictions. These are not just procedures for accumulating correct knowledge. They are procedures for identifying and eventually correcting mistakes. And the mistakes being identified right now, in cosmology, in particle physics, in the foundations of quantum mechanics and gravity, are being identified precisely because the scientific method is working. The instruments are precise enough, the theoretical frameworks are developed enough, and the willingness to follow the data, even when it leads somewhere uncomfortable, is strong enough that the anomalies are visible. That is not a failure of science. It is science functioning as it should, but it requires the recognition that what it is revealing, right now, is the extent of what we don't know. And that recognition, taken seriously, should reconfigure your understanding of where we stand. Let's go somewhere even more specific and even more unnerving for a moment. because there is one result in modern physics that I have not yet discussed, and that deserves direct attention. It is a result from 1931 that is not about physics in the traditional sense, but about mathematics, and therefore, by the implications of the unreasonable effectiveness argument, about the limits of what physics can in principle achieve. It is Gödel's incompleteness theorems. Kurt Gödel proved, with mathematical rigor that has never been successfully challenged, that any sufficiently powerful formal mathematical system, any system powerful enough to express basic arithmetic, contains true statements that cannot be proved within that system. There will always be truths that are beyond the reach of the system's own axioms and rules of inference. And furthermore, the consistency of such a system, the guarantee that it won't produce contradictions, cannot be proved from within the system itself. Mathematics, the language of physics, is irreducibly incomplete. There are mathematical truths that no mathematical proof can reach. The implications of this for physics are contested. Some physicists argue that Gödel's theorems apply to formal axiomatic systems, but don't have direct physical consequences, that the universe might be fully describable by a mathematical theory, even if that theory cannot prove its own consistency. Others, including Roger Penrose, have argued that Gödel's incompleteness is deeply relevant to the nature of mind and physical law, that the human capacity to grasp mathematical truths that formal systems cannot prove suggests that minds are not themselves formal systems, that consciousness involves something beyond computation. Penrose has used this argument, controversially, to motivate his quantum consciousness proposals. Whatever one thinks of those specific proposals, the underlying point, that even our most fundamental tool, mathematics itself, has built-in limitations, should at least give pause to anyone who believes that a complete theory of everything is achievable through formal mathematical physics. There is a possibility that Gödel's incompleteness implies something about the physical universe itself, not just about the mathematical tools we use to describe it, but about the structure of physical law. If the laws of physics are mathematical structures, and if mathematical structures are subject to incompleteness, then there may be physical truths that are simply beyond the reach of any physical theory we could formulate. Not beyond reach because we haven't looked hard enough or built a big enough accelerator, but beyond reach in a deep, formal, provable sense. Physical facts that are true but unprovable, not in a mystical sense, but in the precise mathematical sense that Gödel established. This is speculative. The connection between mathematical incompleteness and physical undecidability is not straightforward, and many physicists dismiss the connection as a category error. But the dismissal may itself be premature, and the possibility deserves more serious engagement than it usually receives in discussions of the limits of physics. We have traveled a long way from the opening statement that something is wrong, and I want to bring that journey back to something more immediate, more personal, more connected to the experience of being alive in a universe that is revealing its own depths in this particular way. Because ultimately, all of this, the Hubble tension and the dark sector and the measurement problem and the information paradox and Gödel's incompleteness, all of it points toward something that is not just an abstract puzzle for physicists. It points toward a fundamental feature of the situation of any conscious being that tries to understand the universe it finds itself in. That feature is the irreducibility of mystery, not mystery as a temporary condition waiting to be eliminated by more research, but mystery as a structural feature of the relationship between a finite mind and an infinite, or at least vastly complex, reality. This is not a counsel of despair. The mystery is not a barrier. It is an invitation. It is an invitation to take seriously the possibility that the universe is stranger, richer, and more deeply interesting than any framework we have yet built to describe it. It is an invitation to hold our categories lightly, to ask genuinely open questions rather than seeking confirmation of what we already believe, to follow the evidence wherever it leads, even when it leads into darkness. The people who are doing the most interesting work in fundamental physics today are, in many cases, the ones who are most comfortable with not knowing, who have resisted the temptation to mistake the absence of an alternative for the truth of the existing framework, who are willing to sit with the full weight of the open questions without collapsing into premature answers. There is a way of thinking about this moment that is not pessimistic, though it is deeply serious. We are living in one of the most intellectually extraordinary moments in the history of our species, We have built instruments powerful enough to see the universe back to within fractions of a second of its origin. We have developed mathematical frameworks subtle enough to describe the behavior of particles at energies that existed only in the first moments after the Big Bang. We have mapped the large-scale structure of the cosmos over hundreds of millions of light years. And in doing all of this, we have accumulated enough knowledge to see clearly, for the first time in history, exactly where our knowledge ends. The frontier of ignorance is now visible in a way it never was before, not because we are more ignorant than our ancestors, but because we are informed enough to see the shape of what we don't know. That is genuinely remarkable. And the shape of what we don't know is, as we have seen, extraordinary. Consider the strangeness of the position you actually occupy. You are a collection of atoms. The atoms, themselves almost entirely empty space, with their mass concentrated in nuclei so small relative to the atom as a whole, that if an atom were the size of a cathedral, the nucleus would be the size of a fly. Those atoms are connected by electromagnetic forces into molecules, those molecules into cells, those cells into tissues, organs, a nervous system, a body, a mind. That mind is now engaged in an attempt to understand the universe that produced it, to turn the universe's own processes back on themselves in an act of self-examination. The universe is using you to look at itself, and what it is finding, when it looks, is that the looking is more complicated than it assumed, the looker is more constrained than it knew, and the thing being looked at is deeper than any looking has yet reached. The Hubble tension tells you that space is expanding at a rate that contradicts itself, depending on how you measure it. The dark sector tells you that 95% of reality is invisible to every instrument you have built. The incompatibility of quantum mechanics and general relativity tells you that your two best descriptions of the universe cannot both be fundamentally right. The measurement problem tells you that you don't know what happens when no one is looking. The fine-tuning puzzle tells you that the universe appears to have been adjusted to a precision that requires explanation, and no convincing explanation exists. The information paradox tells you that the most unbreakable principle in quantum physics may be violated in the hearts of black holes. The arrow of time puzzle tells you that the flow of time, the most immediate feature of your conscious experience, traces back to a mystery about the initial conditions of the universe that current physics cannot explain. Each of these is real, each of these is unresolved, and each of these is pointing at the same underlying truth. We were wrong about the universe, not wrong about the details, wrong at the level of the framework. And the wrong framework wasn't a mistake born of laziness or lack of intelligence or insufficient rigor. It was the wrong framework because it was the best framework available, and science, at any given moment, can only build with the materials at hand. Newton was not wrong to assume absolute space and time. There was no evidence in his time against it, and the framework produced extraordinary results. The physicists of 1890 were not wrong to believe their picture of reality was essentially complete. The anomalies were small and the successes were spectacular. The architects of the Standard Model and the Lambda CDM cosmological framework were not wrong to build the edifices they built. The observational confirmation was real, and the explanatory power was genuine. They were working at the frontier of knowledge with the best tools available, as scientists always do. And now the frontier has moved, the anomalies have multiplied, and the tools are showing their limits. This is not a failure of science. It is science. It is exactly what science does. But you should understand what it means. It means that the confident, triumphant narrative of scientific progress, the story where humanity steadily discovers the true nature of reality, chapter by chapter, until the book is essentially complete, is not quite right. The book is not nearly complete. The chapters we have written are genuine and important, but they describe only a small portion of the territory, and the portions they don't describe are not peripheral regions but central ones. The nature of 95% of the universe's energy content, the physics at the Planck scale, the reconciliation of quantum mechanics and gravity, the correct interpretation of quantum mechanics, the explanation of fine-tuning, the origin of time's arrow, the connection between the physical and the conscious. These are not footnotes. They are the main text, and we have not written them yet. What comes next is genuinely unknown. Not unknown in the sense that we have a good guess and just need to confirm it, but unknown in the sense that the people who have spent their careers trying to figure it out genuinely don't know. They have candidates, approaches, intuitions, mathematical structures that seem promising, but they don't know. And this not knowing is not a temporary condition that will be resolved by the next round of LHC data or the next cosmological survey, though those will certainly be informative. It is a deep not knowing that may require the kind of conceptual revolution that happens once every several generations when the accumulated weight of anomalies finally forces the abandonment of old categories and the invention of new ones. Those revolutions cannot be scheduled. They cannot be produced on demand. They arise when the conditions are right, when the anomalies are sufficiently clear, when the old framework's failures are sufficiently undeniable, and when someone with the right combination of technical skill, conceptual flexibility, and willingness to be wrong happens to look at the problem in the right way. In the meantime, the universe continues doing what it does without reference to our frameworks or our confusion. Galaxies are receding from each other at a rate that no theory has correctly predicted. Black holes are evaporating, in Hawking's calculation, and doing something with the information they contain that no one has correctly described. Quantum fields are fluctuating in the vacuum of space with an energy that doesn't match any calculation and drives the accelerating expansion of everything. Virtual particles are popping in and out of existence in the space between your fingers and between galaxies and in the vicinity of event horizons, following quantum rules that are precisely confirmed and completely uninterpreted. The universe is doing all of this indifferently, completely, without caring whether we understand it, without adjusting its behavior to conform to the frameworks we have built, without offering resolution to the contradictions those frameworks have uncovered. And somewhere in all of this, in the gap between what we measure and what we understand, in the space between the equations and their interpretation, in the distance between the map and the territory, there is something that might be the most important discovery of the next century of physics, or the next millennium, or perhaps never. A deeper structure, a more fundamental description, a framework that makes the quantum and the gravitational not two incompatible descriptions of the same reality, but two faces of a single coherent picture. A framework that explains why the constants have the values they do, or replaces the question with a better one. A framework that tells us what dark matter and dark energy actually are, or shows us why we were asking the wrong question in thinking of them as things at all. Whatever that framework is, it will not look like what we currently have. It will be to our current physics what our current physics is to Newtonian mechanics, deeply different in its foundations, containing the older framework as an approximation, and revealing the older framework's assumptions to have been wrong in ways that were invisible from within them. The universe has been here for 13.8 billion years. It will be here, in some form, for an incomprehensible time to come. The stars will burn and die. The galaxies will drift apart as the accelerating expansion carries them beyond each other's light horizon. The black holes will evaporate over timescales so vast that the number of years has more digits than there are atoms in the observable universe. And through all of that, the fundamental laws, whatever they actually are, at the level we haven't yet reached, will continue operating. The mathematical structures, or the information patterns, or whatever it is that physics is ultimately describing will continue doing what they do. The universe doesn't need us to understand it in order to be what it is. It is what it is, fully and completely, regardless of whether any mind has succeeded in capturing it in an equation. And yet minds try. Your mind right now is trying. The physicists and mathematicians and philosophers who are working on these problems are trying. The entire history of science is a record of that trying. Imperfect, incomplete, repeatedly wrong in important ways, and yet producing, through each revision and each new anomaly and each overthrown framework, a picture that reaches further than the one before it. The project is not finished. It may never be finished in the sense of arriving at a final, complete, unrevisionable description of all of reality. But the reaching continues, and the reaching matters, not just instrumentally, not just because it produces better technology, but because the attempt to understand the universe one finds oneself in is one of the deepest and most distinctively human activities there is. It is what it looks like when a mind takes seriously the fact that it exists in a universe and cannot rest until it understands what that means. There is a specific experience that comes with the deepest engagement with these ideas, an experience that is difficult to describe, but that anyone who has really sat with the implications of quantum mechanics, or the fine-tuning problem, or the information paradox, or the nature, of time will recognize. It is the experience of the ground becoming less solid under the familiar conceptual furniture of everyday reality. The sense that the table you are sitting at, the walls around you, the sky above, your own body, that all of these solid, obvious, tangible things are floating on a sea of uncertainty about their deepest nature, that the space between objects is not empty, but seething with quantum fields, whose energy we cannot calculate correctly, that the solid objects themselves are almost entirely empty space, with properties that are fundamentally probabilistic, whose behavior involves a non-locality that stretches across the universe, that the time in which you are experiencing this is not the universal, absolute flow you feel it to be, but a local, relative, possibly emergent, possibly illusory feature of the particular physical situation you inhabit. This experience is not psychologically comfortable, and there is an understandable temptation to step back from it, to retreat to the phenomenological surface of ordinary experience where tables are solid and time flows, and reality is what it appears to be. That temptation is not wrong to indulge much of the time. Practical life requires operating on the surface, using the categories of everyday experience, treating the world as more or less as it appears. But occasionally, and especially in a moment like this one, a moment when the most sophisticated investigations our civilization has produced are revealing deep cracks in the foundations, it is important to resist the temptation, to let the ground be less solid, to notice the uncertainty, to hold the open questions with full awareness of how open they actually are. Because something important happens when you do that. When you genuinely inhabit the uncertainty rather than rushing past it toward the nearest available answer, the universe becomes larger, not physically larger. The scale was already incomprehensible, but conceptually, experientially larger. The space of what might be true expands. The possibilities you can entertain widen. The intellectual horizon recedes. And in that expanded space, the questions feel less like problems to be solved and more like invitations to explore, invitations extended by the universe itself, through the anomalies in our data and the failures of our theories, toward a deeper engagement with what it actually is. This is perhaps the most honest thing that can be said about the current situation in fundamental physics. Not that we have failed, not that we are lost, not that the universe is beyond understanding, but that we are genuinely, productively, necessarily lost in the specific way that every genuine exploration requires, at the point where the map ends and the territory continues. The map has been extraordinarily well made. It has taken us further than any previous map, and now we have reached its edge, and the territory beyond is real, and it does not look like the how map suggested it would, and the only way forward is to start drawing again from scratch, with different instruments, with greater epistemic humility, and with a willingness to be surprised by what the universe turns out to actually be. And here is the deepest cut of all, the one that sits underneath all the others, the one that all the anomalies and paradoxes and incompatibilities ultimately lead toward. The universe may not be the kind of thing that has a complete description, not because it is too big or too complex or because we lack the instruments, but because the relationship between a part and the whole it belongs to may inherently, structurally, provably preclude a complete internal description. A map of a territory drawn within that territory must leave something out, at minimum the map itself, and the relation between the map and the territory, and the process by which the map was made. A mind that evolved within the universe, using the universe's own matter and energy to build its descriptions, may be in a structurally analogous position, not incapable of partial, useful, even extremely accurate description, but incapable in principle of the final, complete, outside view that a theory of everything would require. This does not close the inquiry, it deepens it, because if this structural limit is real, if there is always a remainder, always an aspect of the universe that escapes every description from within, then the history of physics is not a series of successive approximations converging on a final truth. It is a series of successively richer engagements with an inexhaustible reality. Each revolution, from Newtonian to relativistic to quantum, does not bring us closer to the end of the road. It reveals that the road is longer than we thought, and the next revolution, when it comes, will do the same. Not because reality is hiding from us, not because we are being denied the final answer, but because the final answer may not exist in the form we have been seeking it. The universe may be not a puzzle with a solution, but a mystery with a depth. And the difference between a puzzle and a mystery is that a mystery doesn't end. Think about what you know now that you didn't know, or perhaps didn't feel fully before this exploration began. You know that the expansion rate of the universe contradicts itself by measurements that are too precise to be errors. You know that 95% of the universe is made of things whose nature we cannot identify. You know that our two best theories of physics are fundamentally incompatible with each other. You know that the most successful theory in the history of science, quantum mechanics, cannot be consistently interpreted and does not agree on whether reality exists between measurements. You know that time, the most intimate dimension of experience, has no physical arrow at the fundamental level and may not exist at all in the basement of reality. You know that the constants of nature are fine-tuned to a precision that demands explanation and receives none. You know that information may be the most fundamental thing in the universe, or consciousness might be, or mathematics itself, and we cannot tell which. You know that the questions we are asking may be the wrong questions, posed in the wrong language, using categories that a deeper framework will show to have been naive. And you know one more thing, the thing that all of this adds up to, the thing that the universe has been trying to tell us through every anomaly and every paradox and every irreconcilable measurement, that we were wrong, not about everything, not in ways that erase the genuine achievements of 3 centuries of physics, but wrong in the way that matters most, wrong about having it essentially figured out, wrong about being close to the end, wrong about the scale of what we don't understand, wrong, in a word, about ourselves, about the kind of creatures we are, about the kind of understanding we are capable of, about the relationship between our minds and the universe those minds are trying to comprehend. You are inside a mystery, not a mystery that will be resolved next year, or next decade, or perhaps in your lifetime. A mystery that the best minds of your civilization have been working on with extraordinary dedication and rigor and creativity, and that is deeper today than it was a century ago, not because we have failed, but because we have succeeded enough to see how deep the water actually is. The universe is not smaller than it looks, it is larger. It is not simpler than it looks, it is stranger. It is not more comprehensible than it looks, it is less comprehensible. And the incomprehensibility is structured and real and pointing at something we don't yet have a name for. The scientists who will make the next great leap, whoever they are, wherever they work, whatever revolutionary framework they eventually develop, will not begin from a position of confidence in the existing paradigm. They will begin from exactly where we are now, standing at the edge of what is known, looking out at the full darkness of what is not known, feeling the ground of established understanding giving way beneath them, and choosing, despite the discomfort of that giving way, to step forward into the uncertainty rather than back into the safety of what is already mapped. That step is what science actually is, at its core, not the accumulation of confirmed knowledge, though that is part of it, but the willingness to stand at the edge and look clearly at the darkness and say, this is where the next thing is. We don't know what it is. We don't know how to find it. We know only that it's there, because the light we have is not enough, and the universe is too large and too deep and too indifferent to our comfort to stop at the boundary of our current understanding. The universe is under no obligation to make sense to you. That is the oldest and most bracing lesson of the scientific enterprise, learned over and over in the long progression from Aristotle to Newton to Einstein to the present day. Reality does not owe its comprehensibility to the minds that evolved within it. The fact that it has been as comprehensible as it has, the fact that mathematics works, that experiments can be designed and their outcomes predicted, that the universe runs on consistent rules that can in principle be decoded, is itself mysterious, unreasonably gracious, unexplained. And the fact that comprehensibility has now run in certain directions into walls that don't yield, that is not a betrayal of a promise the universe made. It is the universe being what it is, vast, deep, ancient, and under no obligation to fit inside the frameworks of any mind that briefly inhabits one corner of it. You live in a universe that began with a singularity that current physics cannot describe, that contains predominantly a kind of matter and energy that is completely invisible and unknown in nature, that is expanding at a rate that contradicts itself, that operates by two incompatible sets of rules at different scales, that may have no unique quantum state or infinitely many parallel quantum states, or a structure in which time and space are emergent illusions. That generated, at some point in its 14 billion year history, structures complex enough to ask what it is. And those structures have been asking, rigorously and with great ingenuity, and the answer they are getting is not the neat, unified, nearly complete picture they hoped for. The answer they are getting is, we don't know. More than that, what we thought we knew was incomplete in ways we didn't understand. And beyond that, the not knowing goes deeper than we can currently see.